Hello and welcome. My name is John Horvath, and my presentation today is about using geofoam to reduce horizontal and vertical earth pressures on a wide variety of geostructures, such as retaining walls, bridge abutments, underground conduits. I've divided my presentation into segments. This is to organize things in a orderly fashion, as well as to facilitate viewing by you. This is a fairly lengthy video, so you may find it convenient to watch it in segments. Before I get into the material for this presentation, I'd like to point out that I presume that each of you has a basic working knowledge of the manufacturing, material behavior, and standards that are applicable to not only the usual block molded expanded polystyrene, what I will refer to as EPS block throughout this presentation, but also related geomaterials such as resilient EPS block. A resilient EPS block in the past has been called elasticized EPS block. As these materials are used for geofoam applications involving both small and large strain geosynthetic functions. I strongly suggest that if you're not familiar with this background material, or perhaps you'd like a refresher on it, or to expand your knowledge on it, no pun intended, that before viewing this presentation, I suggest you look at this primer on EPS geofoam that I have posted on my YouTube channel, the same channel where you found this presentation. So I suggest you view this primer before you view the current presentation. Well, with that having been said, let's get into things. I want to start off by giving you an overview of what I'm going to cover today. This presentation is intended to serve as a primer on using different types of geofoam materials and products that either consist of, derived from, or otherwise related to EPS block when used to reduce lateral or vertical earth pressures acting on various types of earth retaining structures, below-grade structures, underground conduits, and shallow foundation elements such as structural slabs over expansive ground. And this would be under both gravity and seismic loading conditions. I do want to point out that I'm using the typical colloquial American English where we use the word lateral to mean horizontal in this application. And also I use the word earth pressures. Really these are normal stresses. Technically a pressure is a stress in a fluid, but as we know from the beginning of modern soil mechanics, we've used the term earth pressures. I think it has to do with the fact that we frequently view earth pressures an equivalent fluid type of basis. So I just wanted to be clear about the terminology I'm using. What I'm going to be talking about today is a very extensive subject, and I can only provide an overview here. This subject has been covered in detail in a monograph that I published back in 2018, and at the end of this presentation I will tell you how you can obtain a copy of this monograph. I've broadly divided this presentation into applications where lateral pressure reduction on earth retaining structures is the primary objective. So this involves pressures in the horizontal direction, versus applications involving below-grade structures, underground conduits, etc., where the vertical pressure reduction is primary. However, before I get into the specific applications, there are several key concepts that are fundamental to what I'm going to be talking about today. So it's useful to talk about these concepts initially, because they pretty much apply to everything I'm going to be talking about in the rest of this presentation. I've divided this discussion of key concepts into several topics, beginning with a discussion of design philosophy. As we know, the fundamental overarching objective in geotechnical engineering design, and in fact in civil engineering design in general, is to prevent failure. We always talk about design to prevent failure as the overarching rule that we follow in many civil engineering disciplines, such as structural engineering, foundation engineering, and geotechnical engineering. And when we talk about preventing failure, this is of the overall system, whether it is either new or existing. And I want to emphasize that one of the real benefits of using geofoam for pressure reduction is that it is extremely useful not only for new construction but existing structures. And that's a real benefit of geofoam. The geosystems I'm going to consider today typically contain a structural element. So we have to separately consider geotechnical and structural failures as necessary. Failure, as we use it in a civil engineering context, the preferred term now is limit state, and I will use the term limit state primarily throughout this presentation. The limit state is broadly defined as loss of function. Function in this case being what does the structure intend to be used for. So the limit state has two forms. We have the serviceability limit state, and this involves displacements and deformations of one or more system components. It could be the geotechnical part, the structural part, of magnitudes that inhibit or prevent entirely the intended performance or function of the overall system. And then we have the ultimate limit state that typically involves a physical rupture or its geotechnical equivalent. We know that coarse soil does not fail in the traditional way that solid materials fail. Rather, we develop a failure surface within the soil. But the ultimate limit state involves physical rupture or its geotechnical equivalent of one or more system components, and this then results in a catastrophic collapse or all or part of the overall system. Well, clearly the consequences of the ultimate limit state are much more critical because we're talking about human health and safety. We're talking about extensive property damage. So the ultimate limit state is much more critical than the serviceability limit state. So design philosophies and various codes that we use have historically focused on the ultimate limit state. It's also, I think, easier to generalize and codify a design for the ultimate limit state as opposed to the serviceability limit state. And this is because the serviceability limit state can have multiple aspects. And these aspects are very specific to a particular application. And more importantly, they're quite subjective. For example, if you have a floor in a warehouse that is settling excessively, in terms of total and differential settlement, it's not all or nothing as to when that floor is usable or not. I've certainly been involved in looking at a number of case histories over the years where this sort of problem has come up, and it might be okay, we can't stock things as high as we used to on the floor, but we can still use it to some extent. The point I'm getting at here is that it's harder, I think, to put the serviceability limit state in a code. And the reason I'm emphasizing this distinction is because, as we'll see, when we use geofoam for pressure reduction, we're really dealing more with serviceability than the ultimate limit state. The fundamental equation governing the ultimate limit state in both geotechnical and structural design is capacity, or resistance, has to exceed the demand or loads. I'm going to be using the terms capacity and demand in my presentation. And the excess in this equation represents safety, and I put safety in quotes because that is always a very subjective concept in civil engineering. But the excess capacity represents safety, and there's two ways, of course, of incorporating safety in the overall system. The traditional way is the allowable stress design. Decades ago, it was more commonly called a working stress design. And this uses the well-known concept of safety factors in order to balance this capacity-demand equation. So the modified version of this equation becomes the actual capacity as reduced by a safety factor has to equal or exceed the actual demand. And the actual demand is using what we nowadays call service loads. So essentially we have a reduced capacity has to equal or exceed the actual demand. The more modern approach is the load and resistance factor design. Some decades ago, when it first started being used, was called the ultimate strength design. And this concept uses load factors on the capacity side and resistance or reduction factors on the demand side to balance this equation. So this general equation or generic equation becomes the factored capacity has to equal or exceed the factored demand. And here, both sides of the equation are fictitious. Essentially, we have a reduced capacity has to meet, equal or exceed a increased demand. Now, using this just generic capacity greater than demand equation for the ultimate limit strength design, structural engineers have historically focused on increasing the capacity side of the equation. They accept the demand side for what it is because in most structural applications, the loads are dictated by nature and thus beyond human control. You can't control gravity, wind loads, seismic loads. They are what they are. So in structural engineering, typically, we have to meet the demand that nature gives us and increase the capacity. Now, the same is true in foundation engineering, but there are some very significant exceptions in geotechnical engineering. And I'm emphasizing this because, as we'll see in a minute, this plays a very, very significant role in the topics I'm talking about in this presentation. In geotechnical engineering, many of the problems, such as earth retaining structures, slope stability, the ground, interestingly enough, is both the primary demand source, but it's also the primary capacity source. So the ground is really influences both sides of this equation, the same ground. And that can be very challenging, especially, I think, for LRFD. LRFD, as is well known, was really developed with structural engineering primarily. Becomes more challenging to apply it to geotechnical engineering because we have the same system, the ground, that is influencing both sides of the equation. But this actually works to our benefit for what I'm talking about in this presentation because it allows for creative, innovative, alternative approaches for satisfying this equation. It basically allows us to do things we can't do in structural and foundation problems where we have to live with the demand that nature provides. I'm emphasizing this because using geofoams in the applications involving earth pressures represents a real paradigm shift in the traditional way that civil engineers have satisfied this equation by increasing capacity. And this because in most cases that I'm talking about in this presentation, the primary focus is on reducing the demand side. We could still increase capacity, but by reducing demand, it gives us a more cost-effective way of satisfying this equation. And this applies to both new construction or existing structures. Now, typically with new construction, we're looking to reduce or minimize the overall cost of construction. However, with existing structures, usually we're looking to increase the margins of safety for the existing structure. So it's a very important paradigm shift where we're focusing on reducing the demand side and not looking so much on the capacity side, because it's a real marked departure from the traditional design philosophies and requires that both design professionals and academic researchers look at things from an entirely new perspective. And I say that as one who was involved in academia as an instructor for over 30 years. I certainly know what we teach civil engineering students on both the undergraduate and graduate level, that we tend to focus on increasing capacity and simply accepting demand as it is. But it's a real shift in design philosophy to focus on the demand side. So we need to look at things from a fresh perspective. That's what I'm getting at here. Next topic I want to talk about is the design for earth pressures. As I noted in the preceding section, because geotechnical problems involving earth pressures, the ground is both the primary source of demand and capacity. This allows us to have a broader range of potential design solutions compared to structural and foundation engineering, where we're dealing with unchangeable natural phenomena as the demand side. So central to developing design solutions for geotechnical problems involving both lateral and vertical earth pressures is that these earth pressures vary as a function of displacement relative to some initial geostatic stress state. Now, the geostatic stress state is not fixed, as defined by K sub O, coefficient of lateral earth pressure at rest. It depends on a site stress history as well as changes that may be the result of a construction. For example, if we do artificial compaction as we're placing backfill and fill materials. We can have further complications because depending on a soil's mineralogy and particle size distribution, these earth pressures can also vary as a function of water content. And this variation tends to be site-specific, natural, seasonal, as well as changes in the fluid flow boundary conditions as the result of construction. For example, we permanently cover the ground surface with a pavement or a building, or we add or remove natural vegetation from the ground surface. There's no shortage of papers talking about something as somebody went out and cut down a tree, and just making that change in the environment caused soils to shrink and swell. So the point I'm getting at here is that although earth pressures are a natural design demand, the magnitude of that demand is not fixed or static, and it's going to vary substantially depending on site and application-specific displacement. And again, I'm focusing on displacement. This ties in with what I said previously about the serviceability limit state, that I think you see where I'm going in this presentation is that really it's the things I'm talking about here are displacement driven. They're not strength driven. Another important point to make is that the demand that's caused by earth pressures can be self-reducing, at least to some extent, provided the overall system allows for the ground to displace in a manner and direction so that this self-reducing behavior can develop. What I'm talking about self-reducing is, for example, the at-rest state can go to the active state if we allow the ground to move in an appropriate direction. So this is further adding to the complication, because we've already identified the fact that the ground is both the demand and the resistance, and we now indicate that that demand is not a fixed quantity. It could vary with a number of things, primarily displacement. Now, when a structural element is placed in contact with the ground, it can affect as well as be affected by the geostatic stresses, depending on the displacement-related boundary conditions of that application. Now, historically, when we think about structural elements such as earth-retaining structures and, retaining walls, bridge abutments, as well as underground conduits, they are universally designed to react to the ground as opposed to causing the ground to react to them. So if we look at a cause and effect, the earth retaining structures, underground conduits, etc., are typically designed to react to and accommodate whatever post-construction stress state exists within the ground. So the ground is in control here in determining the loads on the earth retaining structure, underground conduit, etc. There are not insignificant cost and performance issues associated with this. We need to recognize that any time a structural element is placed in the ground, the overall ground structure system is fundamentally a soil structure interaction problem. And to make it clear, I know that there are some people who just use the term soil structure interaction for seismic loading. I personally have never seen the logic to that. To me, soil structure interaction applies to gravity loading as well as seismic loading. So I use it in that broader context here. What I mean is that in addition to satisfying force and moment equilibrium, we have to satisfy displacement compatibility between the ground and whatever structural element, retaining wall, conduit, etc. And we need to do this at least in a qualitative way, if not quantitative. As a minimum, this means we need to consider the appropriate stress state in the ground, active, at-rest, passive, that should be used in design, even if you don't sit down and calculate displacements. So for example, if you had some sort of earth retaining structure, when you're designing it or assessing it, if it's existing, the first thing you need to ask is, can this structure inherently displace on its own? We may not calculate that displacement, but we need to make at least a qualitative displacement. If it can displace, such as a retaining wall, we'll typically design it for the active earth pressure state. But if it can't displace, for example, a basement wall of a building, a bridge abutment, then we should logically design it for the at-rest state. So the point I'm getting at is we do need to consider displacements, even if we don't calculate them explicitly. Well, the use of geofoam, and sometimes, as we'll see, we use other geosynthetics to reduce earth pressures, and this is both lateral and vertical, really represents a very significant paradigm shift from this traditional way of practice that we've followed for the last century or so. First and foremost, because we introduce geofoam into the system, this allows the structural element through the geofoam product to control the earth pressures and not the other way around. So this is a very, very significant paradigm shift from what we've been doing for a very, very long time. Instead of simply saying, look, these are the earth pressures, let's design for them, as soon as we introduce geofoam into the system, we're now letting the structural element plus the geofoam determine what the earth pressures are going to be. And again, in the context of the fundamental equation of design that I talked about a few slides back, overall the focus is on reducing the demand side of the equation. It's a very different way of thinking from what we've been doing historically. Now, this turns out to be particularly useful when we're dealing with an existing structure where we're looking to increase its safety margin. For example, I know here in the New York State area, one of the significant, or just the East Coast of the United States in general, in recent decades, we've been assessing a very large inventory of existing structures for behavior under seismic loading. And these older structures were never designed with seismic loading in mind. So when we evaluate these existing structures, we're looking to increase the safety margin under not only gravity, but now under seismic loading as well. And as we'll see, by using geofoam, it allows us, in many cases, to satisfy this desired increase in safety margin with little or no change to the earth retaining structure itself. Another important element of using geofoam to control earth pressures is that because this is inherently a soil-structure interaction problem, we need to consider displacements much more explicitly. And that's because the geofoam component is always designed on a stiffness, in this case, force displacement basis as opposed to strength basis. Again, traditionally, if you were designing a freestanding retaining wall for the active earth pressure state, we would say, okay, what's the unit weight of the soil? What's the phi angle of the soil? The strength of the soil? Well, now if we introduce geofoam into the system, it is always a stiffness-based design. The strength of the ground per se does not govern the design. So to sum things up to this point, when we use geofoam to reduce earth pressures, whether lateral or vertical, really requires a whole new way of thinking. And that means we need new zero-based analytical methodologies for design. We really can't use analytical methodologies that we've used historically. Well, the next general topic I want to talk about in this discussion of key concepts is geofoam functions. Well, as is well known, any geosystem that uses geosynthetic products should always follow the well-known precept of design by function for the geosynthetic products that are used. This seems very obvious and logical to us now, but having been around in the earliest days of geosynthetics usage, certainly was not followed. The primary geofoam functions that are used to reduce earth pressures are discussed in detail throughout the remainder of this presentation. So I just want to highlight two broad issues here. Number one, as a group, EPS-based geofoams are extraordinarily multifunctional. Much more so than any other geosynthetic product category, such as tensile reinforcement or geomembranes, things like that, that typically have one or at most very few functions. For example, geogrids, they only do one thing, tensile reinforcement. That's not to belittle them, but that's all they do. Not only are the geofoam functions many in number, they are also unique to geofoam. They tend not to replicate what other geosynthetics do. The reason I'm emphasizing this is that this inherent multifunctionality of EPS-based geofoams is overall certainly a benefit because it allows us to use these materials for many different applications. But it's not possible to turn off a function if they're not going to be used in a given application. And this always needs to be kept in mind, as these, what I call latent or unused functions, can create post-installation issues if not anticipated and considered during design. So the point I'm making here is you have to keep in mind that EPS-based geofoams can do a lot of things. And even if you only wanted to do one thing in a particular application, you always have to keep in the back of your mind all these other things that it can do. And I'll give you a very significant, very potentially serious example so you see what I'm talking about. And this is the classic example of what we call differential icing of paved surfaces. And this could be a safety issue. There have been fatalities in the early days of geofoam usage in the 1960s and early 1970s when differential icing was not recognized. And this occurs when EPS block is used primarily for the lightweight fill function, something that's very significant in embankments, things like that. If you've viewed my narrated PowerPoint presentation on the Topaz, Idaho project, you know that I talked about this in some detail. It was a very significant consideration on that project. But it does come up in applications in this presentation, which is why I'm mentioning it here in some detail. If you're not familiar with the phenomenon of differential icing, I do talk about it in a research report that you can find on my ResearchGate website. Basically, the source of the problem is, as we know, the surface and near surface area of planet Earth is a very dynamic, ever-changing thermal environment. We have many different forms of heat flowing in and out of the ground surface during the course of a day, depending on the season of the year. Things such as cloud cover, ground cover. Does a slope face north or south? Which hemisphere are you in? Things like that. But the bottom line is there's a net flow of heat flux into the ground. Now this is balanced by what we call the geothermal heat flux that is coming up from the center of the Earth because of the natural inherent heat within planet Earth. And these two are in balance. And the balancing point is ever changing. Okay, so the point at which these two heat fluxes are in equilibrium, it changes throughout the course of a day. It certainly changes from day to day, season of the year. It's moving up and down within generally the upper few tens of feet, several meters of the ground surface. And of course, this is heavily influenced by the groundwater table depth. Well, the problem is when we now come along and we place EPS block geofoam into the ground, this is going to significantly disturb this balance of these two fluxes. And that's because EPS has a thermal resistivity that is about 30 times that of soil. So in very simple terms, if you put 1 meter, roughly 3 feet of block molded EPS in here, it is going to have the same thermal effect in terms of heat flux, heat flow, as about 30 meters or 100 feet of soil. So a little bit goes a long way to disrupting this equilibrium point. Well, experience and research has found that this is primarily a problem at night, right? Because at night you have the ground surface tends to radiate heat from the ground surface. And it's important to understand that when you see a temperature measurement, you see it on your cell phone, you hear it on TV, you see it on a website. That heat is measured 2 meters or about 6 feet above the ground surface. So the standard place for measuring temperatures for reporting weather around the world is 2 meters above the ground surface. It's very important to understand that the heat at the ground surface can be very, very different. And this happens at night where we've placed geofoam, EPS geofoam in the ground. which is basically in the duration of the nighttime hours, this foam is going to effectively completely block off the geothermal heat flux. So it's going to allow the ground to give up much, much more heat than it would ordinarily be able to do, because we've now eliminated this source of heat here. So what happens is you could get a surface temperature of the ground that is substantially lower than the official air temperature. So you can have an official air temperature that is several degrees, and whether it's Fahrenheit or Celsius doesn't much matter, can be several degrees above freezing, and yet you can have a ground surface that is at or below freezing. I'm sure we've all gone out to a car on a cool or winter morning, and we see the vehicle coated by what we call hoarfrost, kind of a light white coating of frost. And essentially what happens is the body of that motor vehicle cools down more than the air during the night, because it's nicely insulated from the ground surface by the tires. Well, what is simply a nuisance when you have hoarfrost on your car can really become a safety hazard on a roadway, because it creates black ice. And the reason this is called differential icing is because what happens is that if you have a roadway that just has earth beneath the pavement, and then all of a sudden you transition to a segment that for some reason has EPS block geofoam beneath the pavement, you can have a vehicle driver who's going along, the pavement is dry and not a problem, and all of a sudden they're coming along at roadway speed, and they hit this black ice quite suddenly that has formed over the portion with the EPS geofoam. And you see here an example from the early 70s in Norway where this occurred. And as I said, this was found to occur first in the late 1960s, early 1970s, when geofoams were being used as pavement insulation. And I know certainly here in the United States that there was at least one case where there was fatalities associated with this sort of thing. We know how to design for this now when we use EPS block geofoam, but this is an excellent point I'm getting at. We may be using the EPS block geofoam as a lightweight fill for an embankment, or as we'll see in an earthwork application, earth retaining structure application, but we may not be using the thermal insulation function of that geofoam, but we sure need to keep it in mind during design. The second general point I want to make about geofoam functions is that for pressure reduction, there are both small strain and large strain geofoam functions, and there's an order of magnitude strain difference between the two. This multi-strain functionality of EPS block and its derivative materials, such as resilient EPS block, are really quite unique among geosynthetics, which tend to be what I call one-trick ponies in terms of an operational strain range under service loads. I mean, we all know, for example, if we are designing, say, a mechanically stabilized earth wall that is using GeoGrid, that there's kind of a magic strain level that we've settled on to design for. So there's a very limited strain range that we look for in design of that GeoGrid. Certainly, we don't typically have GeoGrid installations where, in one case the strain is 2%, in another case it's 40%, something like that. What we do with geofoam for pressure reduction. Well, the relevance of this to this presentation is that there is no one geofoam material or product, EPS related or otherwise, that is the most efficient to use in all functional applications. And this is entirely separate from the fact that you can mold EPS block in different densities, as we know. I'm emphasizing this and I will emphasize it again because one of the many bad habits that have developed in using EPS-related geofoams for pressure reduction is that there's a way of thinking that there's one product can do it all, and that is simply not the case. Not in a cost-effective, efficient way. I mean, if I could use a simple analogy, if you were designing a building, could you design every building using structural steel? Yeah, I guess you could in principle. Is it always the most economical to do that instead of using Portland cement concrete or perhaps nowadays even wood? No, of course not. You evaluate which material is the most cost effective for a particular project. And it should be that way when using geofoam to reduce earth pressures. So for every geofoam application, there's typically one specific geofoam material and related product that's the most cost effective to use. Unfortunately, as I already noted, there's this urban myth that has evolved in the last couple decades that block molded EPS is a one-size-fits-all geofoam material and product. And this really persists globally to the present. And having been involved with geofoam since 1987, so for certainly over 30 years now, I could tell you from firsthand experience that this is really primarily due to the failure of the EPS industry, at least here in the United States, to educate design professionals and academic researchers for that matter to the pros and cons of each geofoam material and product, as well as the failure of both academic researchers and design professionals to do due diligence to educate themselves about different types of geofoam materials and products. This information has been out there. I mean, I wrote a book 25 years ago that talked about all the different geofoam materials and products, not just EPS. I talked about extruded polystyrene, glass foams, concrete foams, a wide variety of geofoam materials and products. So I think people have gotten lazy about, they find something that works and they don't really think about, gee, am I serving my client properly by choosing the most cost-effective material? But as I said, I primarily fault the EPS industry, and we'll see why. I'll elaborate on this a little bit later. I am emphasizing this point because this was the subject of a paper that I wrote about 10 years ago. I've seen some, and it goes beyond just inefficient designs. It extends to academic research, where I think the interpretations made by the researchers were significantly flawed because the researchers did not understand the geofoam material and product they were using. They drew conclusions that I think were flawed. And I talk about this in this paper, which this is the link to my ResearchGate site, where you could find this and dozens of other publications related to geofoam and other topics. The last topic I want to talk about in this segment on key concepts is yielding. The term yielding has many different meanings and associated implications in engineering mechanics and civil engineering that depend on the specific context. And I'm pointing this out because the term yielding has been used historically, and this goes back to at least the mid-1980s, perhaps earlier. The term yielding has been used in the context of the topics in this presentation. So it's very important that I clearly define how we use the term yielding as it applies to earth pressure reduction using geofoam. In this presentation, yielding is simply a synonym for normal displacement. And this is a displacement of a system component. It could be earth retaining structure. It could be the soil mass adjacent to that structure. And it's the displacement in the same direction in which earth pressure reduction is occurring. So it's either going to be lateral or it's going to be vertical. As an aside, I wish that decades ago when people started using the term yielding, they simply used displacement. It would have avoided, I think, some confusion. But it is what it is. We can't change what is already out there in the literature, so we simply have to understand what the word yielding means. So depending on the specific application, yielding, as I use it in this presentation, could either be a lateral or vertical displacement. It is also important to understand that it does not imply that this displacement is sufficient or inherently sufficient to mobilize the full shear strength of the soil or some limiting stress state, the active or passive state. We will have some partial strength mobilization, and the stress state will be something then the at rest, but it is not the ultimate limit state for the soil. And I'm emphasizing this because normally when we hear the term yielding in engineering mechanics or civil engineering, we think of a material or a system component that has quote unquote failed, has reached the ultimate limit state. So we also need to understand that yielding, as I use it in this presentation, does not imply displacements or deformations that are plastic or non-recoverable in nature. Again, usually when we see here, oh, you know, that beam yielded, right away one's mind goes to plastic deformation of the material that comprises that beam. That's not inherently and necessarily the case, although, as we'll see, the inherent inelastic nature of the soil can imply some plastic behavior. The next topic I want to talk about is arching. The phenomenon of arching within a particulate or granular material such as soil is broadly related to the structural concept of an arch composed of solid material as being a fundamental load-bearing or load transfer mechanism for some type of structure such as a bridge or a viaduct. Historically, in the geotechnical literature, arching is often referred to as the trapdoor problem, and this was made famous by work done by Terzaghi in the 1930s, or we go back further in time, called the silo problem, that was made famous by Jansen over a century ago. Arching is the predominant geomechanism in many of the applications discussed in this presentation, so it's very important to highlight some of the key aspects of this phenomenon. First of all, arching is, strictly speaking, a two-dimensional phenomenon. If we had three-dimensional behavior, it's more properly called doming, such as the dome of some type of building. However, for simplicity, I'll use the term arching in this presentation to cover both two- and three-dimensional geotechnical behaviors. Now, geotechnical arching is much more varied and complex compared to what we might call structural arching or architectural arching, because in geotechnical engineering we could have both positive and negative arching. Now, positive arching, which is sometimes called simple arching in a geotechnical context, involves when we have soil particle yielding, again, yielding meaning displacement, and the related development of shear stresses and mobilization of shear resistance that is due to some one-dimensional localized yielding of a relatively small concentrated soil mass relative to the larger body of non-yielding soil around it. And in Terzagh's classical trapdoor problem that involved positive arching in the vertical direction. You see in any number of books and publications, the more you lower the trapdoor, the less the stress becomes or pressure becomes directly above the trapdoor, because the soil is settling with the trapdoor, but the soil on either side of the trapdoor is non-yielding. So in positive arching, you get a reduction in earth pressures within the yielding soil mass in the direction of yielding. It's important to understand that load just doesn't disappear. Static force equilibrium forces dictates that if you reduce the earth pressures in one place, you have to increase them someplace else to balance out the forces. So in positive arching, although you get a decrease in pressure above the trapdoor, for example, on either side of the trapdoor, those pressures are going to increase in the non-yielding soil, because that non-yielding soil now acts as the supports for the soil arch, if you will, that develops. In the same way that if you have a arch bridge or an arch viaduct, you're going to have support reactions where that arch meets the ground. Now, negative arching develops when these roles are reversed. And if you, in this case, you have a small concentrated soil mass that is the non-yielding pressure concentrating hard spot, if you will, relative to yielding of soil on either side. As we know, the stiffer you make a system component, it tends to, if you will, attract load. Right? That's a key concept in structural engineering. So really, whether positive or negative arching in a geotechnical context as a geomechanism, it really is an earth pressure redistribution mechanism. Because again, if you decrease or increase the pressure somewhere, that has to be balanced by an increase or decrease somewhere else. Things have to balance out. So although the load doesn't go away, it redistributes, and certainly that can be beneficial. We simply use that redistribution to our benefit. Important to understand that neither positive nor negative arching can develop in a vacuum. It just doesn't happen by itself. There always has to be some sort of initiating or triggering or causative mechanism. And in this presentation, I'll refer to it as induced yielding. So in this case, in the Terzaghi trapdoor problem, when one artificially lowers the trapdoor, that is now the triggering mechanism that is inducing yielding of the soil directly above the trapdoor. So of course, this induced yielding is typically the result of human activity, and I think you see where we're going with this. In this case, the activity that we do is to place the geofoam product in the ground. This is going to be the triggering mechanism to induce arching. Although positive and negative arching in the vertical direction have received most of the attention in the civil engineering literature for over a century, and this relates to the seminal work of Jansen with storage silos and Marston, Spangler, Handy over several generations with underground conduits. Actually, it turns out that arching, primarily positive arching, can occur in the horizontal direction as well. And in reality, it's this horizontal positive arching that is actually much more prevalent in geotechnical engineering than the vertical. It's been a part of the system behavior of a wide variety of geostructures, such as rigid and flexible earth-retaining structures, although this point has not been emphasized in literature, at least to the extent that it should. Specifically, for a very long time, we know that if we have a classical freestanding rigid retaining wall, right, it's something that every undergraduate civil engineer around the world learns about. We do not have a rigid wedge of soil developing behind that retaining wall, as Coulomb simplistically assumed in the 18th century, and many other researchers since then in the 19th and 20th centuries, and even to the present in the 21st century. But really, it's a deformable soil mass, and you get arching developing within that soil mass. And this has been shown theoretically by researchers such as Handy and Harrop Williams in a variety of published papers in the latter decades of the 20th century. But despite this, there's countless generations of civil engineers still cling to that hoary old chestnut of a simplistic triangular distribution of active earth pressure behind a retaining wall, even though Terzaghi showed almost 100 years ago that is simply wrong. I mean, we've known it's wrong for a long time, but it sure is easier to assume a simple triangle, and we still do that. Well, if you want to advance the state of practice, especially with using geofoam for earth pressure reduction, we have to sacrifice this simplicity and ease of use and do things that are more theoretically accurate. Well, I now want to move on to the next segment. It's the first of several segments in which I will talk about reducing lateral pressures on earth retaining structures. And in this first segment, I'm going to present an overview, and then we'll get into some of the very specific designs. And in this overview segment, I've divided this up into 4 topics. Beginning with an introduction. There are 2 fundamentally different geofoam functions that can be used to achieve lateral pressure reduction behind an earth retaining structure. And I would say that probably the vast majority of civil engineers only know about one of the 2 at the present time. The one they probably don't know about is what we call the compressible inclusion function. And this is a geosynthetic function that is unique to geofoams, and not all geofoams do this well. As you can see, and I'm just using this very simple example of a freestanding retaining wall with retained soil. This is just simplicity for illustration purposes. A geofoam compressible inclusion is basically a relatively thin panel of material, and by thin, just to put some rough numbers on things, we're talking about material thickness that's maybe only 6 to 12 inches. All right, so about 150 to 300 millimeters thick, provided it's the proper material. And so there's a caveat with that. It's got to be the correct material to use. All right, so this is our compressible inclusion, as we call it, and this is a large strain function. It is one of the relatively few large strain functions of geofoams. Most geofoam functions are small strain functions. And by large strain, we're talking about double digits, 10, 20, 40% strains. The other functional usage is called lightweight fill, and I suspect this is the one that the vast majority of people viewing this presentation are familiar with, at least to some extent. And this involves the stair-stepped placement, and this stair-stepping is really essential. Stair-step placement of EPS blocks behind the earth retaining structure. And although I'll touch on this more later, both of these can be used with both new construction as well as to retrofit an existing structure. This stair stepping is essential, and I emphasize that because if you look at some of the early magazine articles, for example, that talk about EPS geofoam, you will see that these blocks were placed with a vertical face. And we now recognize that that is not the way to go. All right, so we have a much more substantial, I think you can see volumetrically that, if this is roughly a one-on-one, let's say for discussion purposes, the volume of geofoam that has to be used here is orders of magnitude greater than in this relatively simple panel we see here. And this is a small strain function, as most geofoam functions are. It's essential to understand that the compressible inclusion and lightweight fill functions are competitive when it comes to reducing lateral pressures. They are not complementary. And the reason is that in most potential applications, each provides an alternative solution to the same problem. So what I'm getting at is basically you could get to the same endpoint with either approach. So these are really competitive technologies. In the vast majority of applications, the compressible inclusion alternative is the default choice, simply because they can get the job done with a lot less material as well as construction cost. I mean, it's very easy to place a relatively small panel of material manually. You don't need any heavy construction equipment to do this, for example. And obviously the material volume and therefore material cost is a lot less. And with the compressible inclusion function, as you'll see, you easily can incorporate fluid drainage into the geofoam product. And this would be desired in most applications. You want to allow for the drainage of any water that infiltrates the retained soil and possibly ground-borne gases as well. However, which function you use, compressible inclusion, lightweight fill, should always be made by a knowledgeable design professional and based on project-specific assessment of both technical and cost considerations. The point is there's never a one-size-fits-all solution to the problem. Well, unfortunately, to date, we rarely make this project-specific assessment of compressible inclusion versus lightweight fill. And that's simply because most design professionals and academicians as well, if they're doing research in this area, are ignorant of the compressible inclusion alternative. I alluded to this earlier in this presentation, and I'll reiterate again. The reason really relates to the EPS industry as a whole, especially here in the United States, has tended to promote only the lightweight fill alternative. And, if you go to the websites or, talk to any EPS geofoam molders here in the U.S. supplying geofoam projects, I doubt you will find them saying anything about the compressible inclusion function. They really have not tried very hard, if at all, to educate design professionals that the compressible inclusion alternative even exists. And it's a very simple reason: money, the proverbial root of all evil, as people like to say. Obviously, there's a lot more money to be made selling a relatively large volume of EPS blocks for a lightweight fill alternative, as opposed to a 6-inch, 150 millimeter thick panel of material for the compressible inclusion alternative. It's really a business decision. And the reason is that expanded polystyrene is a classical generic commodity material. The patents on it have long since expired, decades ago. Anybody anywhere in the world can make EPS blocks. It's actually, compared to making other types of geosynthetics, it's one of the easier industries. If you wanted to get into the EPS block molding business, it's a lot easier than getting into the business of making geogrids or something like that. So whenever somebody is selling commodity materials or products, whether it's paper clips or whatever, the profit margins tend to be relatively thin, relatively modest, and the only way you're going to get ahead in business is to sell a lot of volume. So it's a volume-driven business. So this informational gap between the lightweight fill and compressible inclusion alternatives, it's simply because, let's face it, EPS block molders want to sell you and your client a large volume of EPS so they can make some money. Now, before I examine these two functions separately and in each of their separate segments, in this overview, I want to discuss three areas that these functions have in common. First, I want to talk about the problem variables that should be considered when you make a site and project specific design assessment. I want to talk about an overall framework of a site and project specific design process. And I want to talk about the different metrics, numerical metrics we can use to assess the load reduction efficacy of a design alternative. I mean, we'd like to be able to quantify, okay, if we use geofoam in some fashion under gravity or seismic loading, what benefit are we going to get from that? We'd like to be able to quantify that benefit. First, considering the problem variables. While certainly if you're thinking about lateral pressure reduction, your mind should go to, first and foremost, to the compressible inclusion function. That's going to be your baseline de facto choice in most applications. Certainly, I'll be the first one to say there are situations where the lightweight fill function may be more advantageous technically. So what are the key problem variables you should consider on a site and project specific basis? Well, first of all, what kind of earth retaining structure you're talking about? Is it new construction versus existing? We're talking about a rigid earth retaining structure versus flexible. Although the vast majority of pressure reduction is with various types of rigid retaining walls, basement walls, bridge abutments, certainly there have been some applications with, say, with anchored bulkheads, for example. What is the inherent displacement potential of the earth retaining structure? And what I mean by inherent is, look, if I built this earth retaining structure without geofoam, is it inherently non-yielding, yielding, or self-yielding? So for example, if I build a basement wall of a building or a bridge abutment, well, without geofoam, that's inherently non-yielding. That earth retaining structure simply cannot move horizontally because of structural restraint. But if I build a freestanding retaining wall, that is inherently yielding. We know that that wall is going to tend to translate or slide and rotate under the earth pressures. It's going to give a bit. You may not be familiar with the term self-yielding. I will explain that a little bit later in this presentation. What are the site constraints? How easy is it to get material and equipment and personnel into a project site, vertically and horizontally? The underlying subgrade material is very important, and this would be a situation where if you had a soft subgrade under the site, well, I'll be the first one to say this is quite probably a situation where you would use the lightweight fill function, because in addition, it will reduce the lateral pressure on the earth retaining structure, but it will also reduce the vertical pressure on the ground that's going to cause settlement or potential instability. With respect to the geofoam itself, are you looking for what we call a full or partial depth placement? I'll elaborate on those later on. What magnitude of lateral force reduction are you looking at? And this is especially important if you're dealing with an existing structure. Again, some retaining wall that was never designed for an earthquake. Now you want to evaluate, you want to achieve a certain threshold of safety under a design earthquake. So you have an idea of how much you need to reduce the lateral force. What type of loading are we dealing with? Gravity, seismic? Are we dealing with expansive soil or rock? And you may need to cycle through these more than once during the design process to fine-tune and converge on your design. Let's talk a bit about the design process itself. Well, there are several aspects to the design process that are common to to both the compressible inclusion and lightweight fill functions for reducing lateral pressures. First and foremost is that you need to consider the external behavior of the overall earth retaining structure, geofoam ground system. This is what we often refer to as global stability in geosynthetic problems. We need to consider the internal stress strain, force displacement behavior of the geofoam component, and the internal behavior of the earth retaining structure as a structural member. This is nothing new. This process of considering these three aspects is something we've been doing for decades now with other geotechnologies such as mechanically stabilized earth walls and segmental retaining walls, where you have to evaluate the global stability of the overall system, the facing, the reinforcement, the soil. You need to consider the performance of the tensile reinforcement, and you need to consider the structural design of the wall or facing elements. So this overall process is not something new. What is a bit different is with both mechanically stabilized earth walls and segmental retaining walls. Certainly in recent years, engineers have gotten used to what we call vendor design systems, where you could say on a contract drawing, look, I want a segmental retaining wall to look like this and go here, and then you leave it up to the contractor to decide which particular wall type they want to use. And typically there are engineers who do the design for the wall manufacturer. This is what we call a vendor design system, where basically the engineer of record for the overall project, she or he is not going to sit down and actually design the segmental retaining wall or mechanically stabilized earth wall. This option does not exist at present for using geofoam to reduce earth pressures. So when you use these on a project, as the engineer of record, you need to do all three of these things yourself. And you have to develop the appropriate specifications for the materials, the construction, for all the system components. So while the process is something we're used to, having to do all elements of the process may be something that a lot of engineers are not used to. It's safe to say that the internal behavior of the geofoam component is the most important, and at the present time, unfortunately, least understood by both design professionals and academic researchers. Although the geofoam in both the compressible inclusion and lightweight fill functions is doing the same thing, reducing the various earth and surcharge loads that get passed through the geofoam to the earth retaining structure. And you want this to be done obviously in a controlled, predictable manner. The physical mechanisms by which this happens are totally different and unrelated. So the end result may be the same. A certain amount of load gets to the earth retaining structure, but how it gets there, what is happening geomechanically within the system is different as night and day between the two functions. So again, a point I've made previously, because what is happening within the systems is completely different, the most efficient geofoam materials and products to use for these two functions are also completely different. Not the first time and not the last time I'll emphasize this point. There is no universal one-size-fits-all geofoam material and product. And I'm emphasizing this because there are way too many design professionals as well as academic researchers who think you could take a block of EPS and use it for anything, and it's the one and only material and product you ever need to use, and that's simply not the case. Now, regardless of the function, the compressive stiffness of the geofoam under surface loads always governs the design. I emphasize this because we're, especially now with LRFD, we're really used to thinking in terms of strength of materials. And in fact, strength is irrelevant, not only irrelevant, for most geofoam materials, it's ill-defined. Certainly when you test EPS geofoam materials in compression, you do not get a quote-unquote failure. You don't get a material rupture in the conventional, traditional way of engineering material failures. You simply, in very simplistic, colloquial terms, you simply squeeze the air out of the geofoam and it goes back to being solid polystyrene. It simply doesn't rupture in a traditional sense. So strength is irrelevant. In my opinion, LRFD and other strength-based design approaches are completely inappropriate when you use geofoam to reduce lateral pressures on a system. I know there are people who are LRFD fans who feel that you can bend LRFD to fit any design scenario. I really don't feel this is one of them. In addition, the geofoam material properties such as density or unit weight, they're useful for manufacturing quality control or manufacturing quality assurance, but they're basically useless for design. So, don't worry about what the density or unit weight of the product is. That has nothing to do with its behavior for reducing lateral pressures. I next want to talk about load reduction metrics. Regardless of which function we use, reducing loads on an earth retaining structure using geofoam is never an all or nothing proposition. How much load reduction is sought, again, this is whether it's designing a new structure or enhancing the performance of an existing structure, is always a site and application specific design decision. And you always want to compare it to the no geofoam baseline case. That's very important to understand. You always want to say, as a point of comparison, you want to say, well, if I did not use geofoam at all, what would be the safety factor or whatever. So you always need to have a baseline reference case. So we need a metric for quantifying the loads acting on an earth retaining structure that can be calculated for both the no geofoam and geofoam cases and under all types of loading, gravity, seismic, whatever. Earth pressure, earth loads, surface live loads, things like that also. And this metric should be non-dimensional, so it's independent of system of units, and we can apply it universally. That's also important, I think. Well, there's a number of different metrics that different researchers especially have proposed over the last couple of decades. They include lateral earth pressure coefficients, lateral earth pressure distributions, and lateral resultant forces. After, as I said, I've worked with geofoams since 1987, so having worked with this for over 30 years, I've long ago came to the conclusion that the most useful parameter is what I call the relative lateral resultant force, beta. and that is defined as the ratio of P sub H, which is simply the total lateral resultant force from all sources in some application. All right. Earth load, surcharge, gravity, seismic, whatever the load case. And this is divided by PONC, which is simply the theoretical normally consolidated at-rest lateral pressure under gravity loading. So we're using this simply as a universal metric to both normalize and non-dimensionalize the beta factor. So beta is always going to be a dimensionless parameter. I found that using forces instead of pressure distributions or pressure coefficients, as other researchers have used, is really much better, because lateral pressure distributions do not follow the simplistic triangular distributions as generations of geotechnical engineers have been taught. I've mentioned this previously. And also, if you use pressure distributions or pressure coefficients, it becomes clumsy to include surcharge loads as well as deal with seismic loading. So resultant forces are a single, consistent, simple way to evaluate even very complex lateral pressure distributions where you might have contributions from multiple load sources. And as I said, using the baseline, what's the force under a normally consolidated at-rest condition, that's always very simple to calculate in a given application, and it provides a useful way to non-dimensionalize and normalize this factor, beta. Some basic cases and limits of beta. Obviously, beta of 1 represents the baseline no geofoam reference case for normally consolidated at-rest lateral earth pressures. Beta less than 1 means lower force than the baseline. Greater than 1 means resultant force greater than the baseline. A beta cannot be negative, and it does have an upper bound that's defined by the site and application-specific passive earth pressures. And it's very simple to count. If someone wants to say, look, I achieve a 23% reduction in lateral forces or whatever, it's very easy to calculate a number like that using the beta equal 1 as the reference value in these calculations. Well, I now want to get into really the heart of this presentation, discussing these two functions, compressible inclusion and lightweight fill, more specifically in detail, beginning with a discussion of the compressible inclusion function. And again, I have broken this segment up into several topics, beginning with an overview. Well, as I said earlier, the compressible inclusion function is a large strain functional application because the geofoam product is intentionally designed to go relatively large normal strains. We're talking about tens of percent, 10, 20, 40% under service load conditions. It's important to recognize that such strain levels are anywhere from 1 to 2 orders of magnitude greater than the service load strain levels for civil engineering materials in general. If you think about the strain levels when you design reinforced concrete or steel or other geosynthetics. Intentionally designing for relatively large strains of a system component under service load conditions, I think, is really quite rare, not only for geosynthetics, but civil engineering materials in general. And this requires a very different way of thinking for design professionals, as I'll include myself in this. We're simply not traditionally educated and conditioned to such large strain design. Again, if I look back to my own education and over 30 years of being an educator, We don't teach large strain behavior in civil engineering in general, even on the graduate level, simply because it doesn't come up very often. Another real paradigm shift in thinking is creep strains, which are always a significant design issue with polymeric materials used in engineered construction, and especially for geosynthetics. That's one of the first things when you get involved, whether it's geogrids or geomembranes, geotextiles, or whatever. The creep behavior of these materials and products is very, very important and plays a significant role in the various design equations and methodologies that have evolved over the last several decades. Now, most of us, I think, have been taught or picked up the perception that when it comes to geosynthetics, creep is quote unquote bad, and we have to take reasonable efforts to control it or limit it. And again, for relatively small strain applications such as mechanically stabilized earth walls, it's understandable that you want to limit the magnitude of creep for the geosynthetic tensile reinforcement. However, when we use geofoam as a compressible inclusion, creep is good, if you will. It's generally beneficial in most applications, and we should explicitly consider it. And I mention this because, and I'll elaborate on this later on in the presentation, that too often we focus on using material properties for relatively short-term rapid loading. And, certainly we should be considering that this material is going to be in the ground for decades. We should be looking at the longer-term creep behavior because it can make for a more efficient and cost-effective design. As I said, when it comes to compressible inclusions, creep is your friend, if you will, and we should take advantage of it. But it requires a change in thinking. There's no doubt about that. The overarching aspect of all compressible inclusion applications is that the geofoam component is always the most compressible component in the overall earth retaining structure geofoam ground system. And the geofoam component is the product is there to sacrificially crush, but to do this in a controlled, forecastable manner. Right? This is not a random, haphazard, what happens, happens. We want to be in control and to be able to calculate explicitly how much compression occurs. And because of this control, researchers going back to the 1980s have coined the term controlled yielding for this behavior. And that's because, as I just said, the magnitude of the geofoam compression is not left to chance or happenstance, but is rationally and analytically determined as part of the design process. So you take an appropriate geofoam material and product, and you combine it with an appropriate analytical methodology, and you determine analytically and explicitly how much yielding is going to happen in a controlled fashion in a given application. And I'll show you some qualitative examples later on of what I'm talking about. It's important to understand that compressible inclusion applications are always stiffness and not strength-based. So the most important material property for the geofoam product is the operative value of Young's modulus, but it has to be the modulus that is consistent with the strain level that you're working with, and that strain level is both stress and time dependent. And I'm emphasizing this because, again, I've seen published literature from academicians where they're using a geofoam product in their work, and they're using a Young's modulus that is inconsistent with the boundary conditions of the problem that they're looking at. And this has had, in my opinion, a negative effect on the quality of the conclusions that these academicians have drawn from their research. Now, this Young's modulus can be an overall secant modulus or some incremental tangent modulus. It really depends on the analytical methodology that you are using. Now, I'm going to talk about geofoam product stiffness in a separate section at the end of the segment. Because again, and I've made this point before, but it's significant enough that I feel I can't overemphasize it too much. Both design professionals and academic researchers alike don't seem to fully understand that different geofoam materials and products have unique stress strain time behaviors. And I've seen far too many cases that either in a design situation or in evaluating research data that the wrong geofoam material and product was used, and then they proceeded to use the wrong material properties in either the design or the research. And a lot of it has to do with the fact that, again, going back to the fact that the compressible inclusion function is a large strain, large creep application. And the vast majority of data that you see for the behavior of geofoam materials and products is small strain, rapid loading data. So, you have a long-term, large strain, large creep, long-term problem. Clearly, it's wrong to use short-term, rapid loading, minimum creep data. And again, I showed you this paper previously where I addressed this issue. And if you think I'm emphasizing this too much, it's simply from having been involved with geofoams for over 30 years. I've seen some projects that had some significant failures associated with them. Fortunately, these were serviceability limit state type failures. They were not ultimate limit state failures that resulted in effects on humans, but I've seen some serviceability failures that certainly resulted in cost problems, damage to the overall system. So, and as I also said before, I've seen results of academic research that, in my opinion, were completely wrong because the wrong properties were used. So this is a not insignificant issue, which is why I'm emphasizing it. Now, there are two ways in which the compressible inclusion function can be implemented. The basic way that I showed you previously with just the relatively thin panel of geofoam, this is what we refer to as the reduced earth pressure or rep wall concept. And you'll see why in a minute, why this term has evolved. This term goes back to when I coined it in the late 1980s. We also have what I call the zero earth pressure or ZEP wall concept. And the difference is that in addition to the compressible inclusion, we include multiple layers of geosynthetic tensile reinforcement in a traditional mechanically stabilized earth manner. It's important to understand these two alternatives, the rep wall and the ZEP wall, they are complementary. They're not competitive. Obviously, the ZEP wall concept builds on the rep wall concept. That's pretty clear to see. Each has its advantages. Obviously, this costs more because you've got to purchase and install the geosynthetic tensile reinforcement. So there's pluses to each of these. They each have their place. And I'll discuss the advantages in separate sections of this segment. I'm going to also discuss in a separate segment the role that geofoam compressible inclusion plays with what I call self-yielding earth-retaining structures. Self-yielding, and this is a term that I've coined, it is a type of structure that is rarely, if ever, addressed in textbooks, at least in English language textbooks that I used to use in academia, yet in practice is extraordinarily common worldwide. This is clearly a type of earth retaining structure we should be talking about a lot more, even on the undergraduate level, so that an undergraduate engineer, he or she understands from the very early days of their civil engineering education that such structures exist. Well, let me now get into the reduced earth pressure or rep wall concept in some detail. The primary use of the rep wall concept is to induce horizontal controlled yielding and the associated horizontal arching within the retained soil adjacent to a non-yielding, very important, non-yielding rigid earth retaining structure. Such structures would otherwise prevent yielding of the retained soil. So we're talking about earth retaining structures such as the basement wall of a building or a bridge abutment that is inherently not able to displace under earth pressure. So should normally be designed for the at-rest earth pressure state. And in most cases, you'd also want to include a provision for compaction stresses, which would tend to have an increase near the upper portion of the wall. So the use of the geofoam compressible inclusion allows the at-rest state to transform, theoretically at least, to the active state and reduce the earth pressures that would otherwise exist. The actual earth pressure distribution, because we are inducing horizontal arching, is really more parabolic in shape. It differs rather substantially from the simplistic triangle that, as I mentioned earlier, is something we really need to retire to the Geotechnical Hall of Fame, at least if we're going to design more efficient structures with compressible inclusions. And the peak lateral pressure is typically about the 3/4 point below the top of the wall. Well, this load reduction from the at-rest state with compaction stresses to the active state has obvious benefits for both new construction. Obviously, you reduce the cost of the earth retaining structure. Or if you have an existing structure, earth retaining structure, you can increase the safety margins with literal no modification to the existing rigid earth retaining structure. As I said, the role of the geofoam in the rep wall case is controlled yielding because it enables the lateral displacement of the retained soil sufficient for the active earth pressure state to develop reliably, predictably. And that's because the force displacement curve of the compressible inclusion is entirely under the control of the design professional, not nature. So if we look at this problem analytically, and here I'm showing the lateral earth pressure and forces on the earth retaining structure, lateral displacement, and this red dot would be the baseline, in this case, at rest state with compaction stresses. We know from theory and research that the ground has a force displacement curve, so that if we allow displacement up to a certain point, we will achieve the active earth pressure state. So this will tend to plateau, and it will plateau at the active earth pressure state. Well, we can't control nature. I mean, the shape of this curve is dictated by the type of soil, its density, the height of the wall, things like that. All right, this has been researched. What we can control, obviously, is the stress-strain curve for the compressible inclusion. All right? So we see, really putting together some of the thoughts that I've discussed earlier in this presentation. This is a stiffness-based design. If we think simplistically as the retained soil as being a spring, right, because the slope of this curve is just a spring constant, And we can think of the geofoam compressible inclusion as being another spring. And we are simply matching the force displacement behaviors of the spring. So we can't control the ground, can't control this curve, but we can control this curve by selecting the appropriate material and product so that we reduce the forces on the structure to the active state. Right? In this case, and I just showed it a little bit simplistically here, we're basically trying to come up with a compressible inclusion that just matches where this ground curve plateaus at the active state. And we can't control this, but we can control this. Now, obviously, the maximum benefit of the rep wall application is when you have a full depth placement of the geofoam product, as I've showed you. But there are incremental benefits from using what we call a partial depth placement. There are any number of practical applications, both in new construction or existing structures, where it may not be possible due to some site constraint to have a full depth application. So we simply place it for as much of the height of the wall as we can. It's also important to understand that in most rep wall applications, we would like to have the ability to drain the groundwater and perhaps ground-borne gases adjacent to the wall. So we can actually make use of the secondary geosynthetic function of geofoams, insulated fluid drainage, to complement the compressible inclusion of the geofoam product. And I'll talk about specific products a little bit later in the presentation. Now, the rep wall concept was originally developed for gravity loading, has since been extended to include seismic loading. Generally, in the published literature, at least in the English language literature, you'll see this referred to as a seismic buffer. A seismic buffer is nothing magical. It's simply using the rep wall application under seismic loading. But there are a number of researchers who like to use the term seismic buffer, which is fine. Can also use the rep wall concept with expansive soil and rock. Now, in this case, the primary geomechanism is not strength mobilization and horizontal arching, but the fact that swelling pressures decrease from the confined or no swell case with increasing displacement. So you would want the swelling soils to sacrificially crush the compressible inclusion and kind of self-reduce. Again, this is the self-reducing nature of earth pressures, as I mentioned earlier in the presentation. I next want to talk about the zero earth pressure or ZEP wall concept. And again, this is the rep wall concept, but with multiple layers of geosynthetic tensile reinforcement within the retained soil. This is an incremental, material-wise, improvement to the rep wall concept, but there's a substantial or potentially substantial performance-wise increase. And again, we're inducing controlled yielding within the retained soil. And we have multiple benefits. First of all, the presence of the geosynthetic tensile reinforcement will stiffen the force displacement response of the retained soil. Because as the soil yields, it will mobilize the tensile resistance of the geosynthetic reinforcement. Well, this allows the lateral earth pressures to decrease below the active state and, in fact, approach zero in the limit, and that's where the ZEP wall name comes from. So when you have the geosynthetic tensile reinforcement, you are not limited to achieving the active state. And by the way, when I talk about geosynthetic tensile reinforcement, I include all types of metallic elements, strips and mesh, as well as the usual polymeric products such as geogrids and geotextiles. And in my presentations, I always feel the need to make this clear because there are any number of what I call geosynthetic purists out there who, to them, geosynthetic tensile reinforcement is just a polymeric product, like a geogrid or geotextile. I don't see a need to artificially exclude metallic elements. These are all geosynthetic tensile reinforcement. Well, it's important to understand the fundamental geomechanism going on with the ZEP wall concept is not arching, as with the rep wall concept, but as I said, activation, if you will, of the geosynthetic tensile reinforcement in the very classical mechanism of mechanically stabilized earth. And this is a well-established, well-proven behavior from decades of successful use in practice and associated research. So this is, what we're doing here is nothing new. The only new element is we're using the geofoam to allow the reinforcement to activate. So to look at this in a bit of a quantitative fashion, again, plotting lateral pressures and forces on the transmitted through to the ERS versus lateral displacement of the retained soil. If we did nothing, this would be the at-rest state. And as we've seen previously with the rep wall application, we could reduce things to the active state. All right. Well, if we now include the tensile reinforcement, as I said here, we're stiffening the load force displacement response of the reinforced soil mass. And we know that in the limit, if we went to enough lateral displacement, the earth force would go to zero. I mean, that's what happens with a mechanically stabilized earth wall. There's no load on the outside of the wall, no lateral load. And again, here, what's actually kind of interesting is, I said previously with the rep wall application, this force displacement relationship of the ground was kind of dictated by the soil type and density and the height of the wall. So we could only control the compressible inclusion stiffness. Well, with the ZEP wall application, we actually control both aspects. This force displacement relationship of the reinforced ground, this is within our control, at least within reason, as design engineers, right? Depending on what type of reinforcements we use, metallic versus polymeric, what type of polymeric, how closely spaced, et cetera, et cetera. So we can control the shape of this curve, and of course we control the compressible inclusion curve as well. So the ZEP wall application is interesting because we control both of these responses. So really, depending on how soft we make the compressible inclusion, how stiff we make the reinforced ground, we can achieve some very, very significant lateral earth force reductions. So this ZEP wall concept really provides some new tools in our geotechnical engineers toolbox that go well beyond what can be achieved with the rep wall concept. First of all, allows for development of the well-proven mechanically stabilized earth geomechanisms in situations where it would otherwise not developed, such as behind inherently non-yielding rigid earth retaining structures such as basement walls of buildings and bridge abutments. I mean, we've known for a long time, if you put in geosynthetically reinforced soil adjacent to the basement wall of a building or behind a bridge abutment, it's really not going to do much good because the reinforcements can't activate. They can't develop tensile forces. Well, with the ZEP wall concept, they can. We can also use the ZEP wall concept with inherently yielding rigid earth retaining structures. So if we had a classical freestanding retaining wall, well, we know this wall is going to tend to slide a little bit, rotate a bit under earth forces, and develop the active earth force. Well, if we included geofoam compressible inclusion with reinforcement in the soil behind that wall, again, new construction or with an existing wall, the additional lateral displacement that the geofoam compressible inclusion provides is complementary and additive to the inherent sliding and rotation of the retaining wall. So they act together to reduce the forces even more. And again, the ZEP wall concept could be used under both gravity and seismic loading, full or partial depth placement, new construction or retrofit to an existing rigid earth retaining structure. I have not seen anybody use it with expansive soils. That's not to say that it would not have some benefit, but I will leave that to others to look into and research. Well, I now want to talk about this topic of self-yielding walls. Again, self-yielding wall is not something that we're used to seeing in the published literature. It's a term that I coined some years ago. Now, a traditional earth retaining structure reacts either through non-yielding or yielding to the loads applied to it by the mass of the retained soil. Right? We've talked about that already. We want to state it another way. The retained soil is always what I call the active or initiating element. And active here I put in quotes. This is not the active earth pressure. What I mean is that the retained soil is the one that is actively initiating the earth pressure on the earth retaining structure ground system. And the earth retaining structure is always what I call the passive or resisting element. So the retained soil alone dictates the loads on the earth retaining structure, and the earth retaining structure must be designed to resist them. And it's important to understand, if we use the rep or ZEP wall concept, it doesn't alter the fundamental underlying cause-effect relationship. Now, it will reduce the magnitude of the loads. Yes, there is a benefit. But in a rep or ZEP wall application, it is still the soil or the reinforced soil that is the initiating element, and the earth retaining structure is resisting those loads. The geofoam compressible inclusion is just affecting the magnitude of the force transmitted to the earth retaining structure. However, in recent decades, an entirely new type of earth retaining structure ground system has been identified in which these roles, these classical historical roles of who's initiating, who's resisting, are reversed. And it's the earth retaining structure that is the active initiating element. The retained soil is the passive resisting one. So this is a complete role reversal. And this scenario occurs in applications where we have an earth retaining structure that is an integral part of a statically indeterminate structure that is affected by natural regular thermal changes. And these thermal changes are usually seasonal temperature variations, not day to day, but from season to season, winter to summer, for example, in the environment surrounding the structure. And that's important because it means that these variations in temperatures will occur for the life of the structure. And I call these statically indeterminate structures that are expanding, contracting with the seasons, self-yielding earth retaining structures, and to date I've only seen rigid earth retaining structures behave in this fashion. Self-yielding rigid earth retaining structures are a very significant and growing part of earth retaining structure technology. And research that I've done over the last couple of decades has shown this technology could really benefit significantly from geofoam. The most common examples of a self-yielding rigid earth retaining structure are two types of short span bridges, what we call an integral abutment bridge and a semi-integral abutment bridge. There are other examples. These are typically water resources structures, such as a wastewater treatment tank or basin, or a navigational lock. They undergo very similar behavior. Because of the integral abutment bridges, or IABs, are globally very popular and have been for some decades now. They're the single most significant example of what I call the self-yielding rigid earth retaining structure. So I'm going to use an integral abutment bridge as an exemplar to illustrate the physical issues, the technical problems that come from these physical issues with a self-yielding rigid earth retaining structure, and to illustrate how the compressible inclusion function geofoams can be part of the solution to the problems that develop with these types of bridges. Now, this is going to be a lengthier discussion than the preceding rep and ZEP wall summaries, and that's because, in my opinion, the concept of self-yielding rigid earth retaining structures has not been adequately treated in textbooks, at least in the US. As I said earlier, really, this type of behavior is something that even undergraduates should get some exposure to in their education, so they know that this type of structure exists. So there's a lot of geotechnical engineers that I think are not sufficiently knowledgeable about self-yielding rigid earth retaining structures on even a basic introductory level. So I'm going to get kind of elementary here before I get into the geofoam solutions. And that's really to try to fill in some of this knowledge gap that I feel exists. Well, to begin with, it's worth repeating that it's essential to understand that all structures in the self-yielding rigid earth retaining structure category are subjected to regular, repeated, significant environmental changes in temperature. And these changes are natural and therefore beyond human control or regulation. And I'm emphasizing that because I think sometimes as civil engineers we tend to forget that we make some change to a system. We tend to forget that we can't change the inherent basic physics of the problem, which in this case is the seasonal temperature variation. So this means that the fundamental underlying causative mechanism, what makes a rigid earth retaining structure be self-yielding as opposed to yielding or non-yielding, this fundamental causative mechanism will exist no matter what the specific details of the structure ground system are. So, you know, you could change all the details, and I'll give you examples of what I'm talking about, but you can't change the fundamental underlying physics of the problem. So when you have a statically indeterminate structure subjected to temperature variations, there will either be thermally induced displacements of the structure if it is unrestrained against displacement, or thermally induced forces within the structure if it is perfectly restrained against displacement, or some combination of displacement and forces for intermediate conditions of restraint. And these potential three outcomes can never be eliminated. So they have to be important explicit design considerations. It's also essential to appreciate and understand how a specific self-yielding rigid earth retaining structure accommodates these thermal loads or displacements, and what long and short-term structural and geotechnical behavior issues this creates. So it's important to understand that we can have both structural and geotechnical issues, and these issues can occur in the short term or the long term. And again, I'm emphasizing this because from what I've seen with integral abutment bridges, that people have tended to, look at the structural short-term behavior and not adequately look at the long-term geotechnical behavior. And this has created a lot of problems. So, okay, this is just a very simplistic cartoon, if you will, of a traditional short-span jointed bridge. You have the superstructure, and that's highlighted in dark red because that's what is going to be expanding and contracting horizontally, laterally, as a result of the thermally induced displacements. So this So let's say be a bridge deck, depending on the specific type of bridge. I'll just refer to it generically as a superstructure. Now, in traditional jointed bridge, the tendency of the superstructure to want to expand and contract seasonally is accommodated by having bearings on which the superstructure slides and leaving air gaps, we call expansion joints, at each abutment. So the combination of the expansion joints and bearings structurally, emphasis on structurally, and I'm emphasizing structurally because to kind of jump ahead to, it's kind of like if you're reading a book and you jump ahead and read the last page to see how it ends before you start reading it. The point I'm going to be getting at in this discussion is that what the integral abutment bridge concept has done is eliminate a structural problem but create a whole bunch of new geotechnical problems. And these geotechnical problems have not, in my opinion, been adequately dealt with historically. So the combination of the expansion joints and bearings isolates this moving superstructure from the abutments and the retained soil behind each abutment, and the abutment soil system remains fixed in time and space. Okay, and that's a very important element of a traditional bridge. These are going nowhere. These are fixed in time and space. This is moving in the life of the structure. All right, so the abutment ground system is inherently non-yielding. In fact, these abutments should be designed for at-rest earth pressures plus compaction stresses. Unfortunately, I've seen abutments designed for the active earth pressure state, which I don't think is appropriate. But in any event, these are non-yielding. These are not moving. So all the wear and tear due to this expansion contraction involves only the expansion joints and bearings. Well, as we know, there are structural issues, both performance and maintenance with durability, and required maintenance of these expansion joints and bearings. I mean, expansion joints in particular, they take a lot of beating because of the vehicle tire impact. And so these are relatively high maintenance items for the traditional jointed bridge. So the integral abutment bridge concept is clever. It was developed to eliminate these structural issues by structurally tying the bridge deck or superstructure to the abutments. So these are now, one of the names one hears for an integral abutment bridge is U-frame bridge. It's like the inverted letter U, simplistically. But this now becomes a single monolithic structure. And notice that the bearings and expansion joints are gone. So poof, end of structural issues, right? Well, the problem is that now this entire bridge, including the abutments, is now thermally active. So the seasonal expansion contraction that used to be limited to the superstructure or deck now includes the superstructure plus the abutments. Well, unfortunately, the IAB design concept does not mean all maintenance issues are eliminated, because, as I said, we can never eliminate the underlying physics of the problem is this bridge is going to be affected by seasonal temperature change. In reality, what's happened is the maintenance issues are pushed somewhere else, and specifically into the abutments and the soil retained by the abutments. So new geotechnical performance and maintenance issues are created. So simplistically, the integral abutment bridge concept, what it's done is says, okay, we've eliminated a maintenance structural issue, but now we've created a whole new geotechnical issue. Actually, there's two issues, as we'll see, that didn't exist previously with traditional jointed bridges. And it all revolves around the fact that the abutments are no longer structurally isolated and fixed in time and space, but they participate in all thermal displacements. So really the abutments, if you will, go along for the ride. When the bridge superstructure expands and contracts, the abutments are going to expand or move as well because they're structurally connected to the bridge deck. And as I said, this creates a whole new raft of technical issues and maintenance problems that did not exist with traditional jointed bridges. Worth emphasizing, the IAB concept does not eliminate maintenance problems. It simply relocates them from one part of the bridge ground system to another. And if you think about it, this makes sense because, again, you cannot and never could eliminate the basic physics of the problem. You have a structure that is subjected to seasonal temperature change. You're never going to eliminate that. So I think it's delusional to think that, well, I've eliminated the problems with expansion joints and bearings, to think that all your problems have gone away. As it turns out, all you've done is create new problems somewhere else. But as we'll see, there are relatively simple ways that these can be fixed. So I don't want to denigrate the IAB concept. I think it's very sound and it's probably a way to go in most cases, because the geotechnical problems that are now created are relatively easy to fix. If you fix them once when you're building it or retrofitting the bridge, then they're fixed forever. You know, it's not like the traditional expansion joints and bearings that you'd have to come back and service for the life of the structure. These new geotechnical problems that are created, if you do it right, you could resolve these problems once and for all up front and not have to deal with them again. So the remainder of this discussion of self-yielding rigid earth retaining structures is how and why these problems occur with integral abutment bridges and what could be done about it using the compressible inclusion function of geofoams as the heart of the design concept. So as I said, the thermal displacement of a IAB superstructure is transmitted directly to the abutments, which will undergo an annual displacement pattern. And this pattern is a composite of the translation and rotation about base displacement modes of a rigid earth retaining structure. We know that traditional yielding rigid earth retaining structures have three possible modes. One is translation or sliding. One is rotation about the base. The other is rotation about the top. So this has translation and rotation about the base components. So in the summer, the expansion of the bridge superstructure is going to push the abutment into the retained soil. As the bridge deck cools down in the winter, it's going and contracts. It's going to pull the abutment away from the soil. All right, so we see this back and forth type of rocking behavior. Well, the net result is that although the structural expansion joint bearing problems have been eliminated, they've been replaced by not one but two distinctly different geotechnical problems. Although there's two different problems, the overall mechanism of seasonally the abutments going back and forth is the root cause or source of both problems. But because there are two distinctly different geotechnical problems, each requires a separate solution. However, these solutions obviously have to be complementary. We don't want them to be at cross purposes, and hopefully synergistic. So if we put them together, the sum of the parts is more than either part taken individually. Well, the first geotechnical problem with integral abutment bridges is one that has been recognized since early on and is typically addressed in design. And this is the increase in lateral earth pressure within the retained soil that happens every summer. So simplistically, if we assume that initially after the IAB is built, we have at-rest lateral earth pressures, In the summertime, as the bridge deck expands and pushes the abutment into the soil, these earth pressures are going to go from the at-rest state and trend toward the passive state. And there's been a fair amount of research to analytically and experimentally come up with pressure diagrams to design for this. So this is something that integral abutment bridge designers have known about for decades. This is not a new concern. But they typically, traditionally, they simply design the abutment to take this higher earth pressure. What we'll see is there's a better way to do things. Well, the second integral abutment bridge geotechnical problem, and one that I feel has been much less appreciated historically, begins with the winter season contraction of the bridge deck that pulls the abutment away from the retained soil. Well, this allows obviously the retained soil to expand laterally because, unlike with the traditional jointed bridge, where this abutment was fixed in time and space, it's no longer that. So this abutment can no longer retain the soil as it did with jointed bridges. So the soil expands laterally. The earth pressures will tend to go to the active state within the retained soil. So you might say, well, that's a good thing. Yeah, but the bad thing is what happens is that we're going to have soil that slumps downward against the inside face of the abutment. So yes, the reduction of earth pressure is not bad. It's a good thing, if you will. But the fact that we're pulling the abutment away from the soil is going to allow the soil to slump downward. Well, as we'll see, this has a couple of negative consequences. And as I said, this slumping occurs because the abutments no longer provide a temporarily fixed support and containment of the retained soil, as with traditional jointed bridges, where these abutments are fixed in time and space. Well, unfortunately, as we know, the stress-strain behavior of soil is inelastic and hysteretic, meaning we get these hysteresis loops of loading and unloading and reloading. So at the end of an annual thermal cycle, we saw how in the summer the abutment gets jacked into the soil and the winter it gets pulled away from it. So at the end of one annual thermal cycle, the problem is the abutment will never return to its initial position. And that's because in the winter the soil has slumped down. And because soil is inelastic, come the end of the cycle, it's not going to magically push that soil back into place. That also means that the lateral earth pressures are not going to return to the original initial at-rest state. So the long-term trend is for this net inward kind of marching or displacement of the abundance to increase over time with each annual thermal cycle. So with each one of these thermal cycles in the summer to winter to summer to winter, you will find at the end of the cycle, the abutment keeps marching inward away from the retained soil. What that means is that the average lateral earth pressure in the abutment will increase over time. It may start at the at-rest state, but over time, because the soil keeps slumping down, 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 at equilibrium, this lateral earth pressure is going to be greater than the at-rest state. So every summer cycle now is going to begin at a higher lateral earth pressure than the earth at-rest state, as with the first cycle. Well, the subsidence adjacent to the abutments is also going to increase with time, which makes sense. If the abutment keeps moving inward away from the retained soil, it's understandable that the retained soil is going to just keep slumping downward against the abutment. Well, the primary outcome of the ground subsidence is the development of a settlement trough adjacent to the abutment. And it's not only permanent, but will increase both in depth as well as its lateral extent over time with each annual thermal cycle. Well, if there is no approach slab to the bridge, you'll get this characteristic bump at the end of the bridge. it creates a real rideability issue. If there's an approach slab, you can actually get a failure of the approach slab. I've seen case histories where if this gap underneath the approach slab keeps growing laterally, at some point the approach slab was simply never designed to bridge over that open gap and will simply fail in flexure. And I've seen case histories where this has happened more than once. This, as a secondary outcome of the ground subsidence, is that, as I noted previously, each summer season begins not at the at-rest state, but some horizontal earth pressure that is greater than the at-rest state. And this is a soil mechanics phenomenon that is technically known as ratcheting. That which, with each back and forth, back and forth, back and forth cycle, you are beginning each new cycle at a greater and greater and greater earth pressure. So that in the summer, as you jack this into the soil, it's going to go up and up and up and up. And this will increase, continue to increase over time. The research has shown this doesn't just stabilize at some point. It just continues to increase over time and can lead to structural distress of the abutment. Because, as I said, although bridge designers have known from early on that, okay, I've got to design the abutment for a higher lateral earth pressure in the summer, they think that summer lateral earth pressure is going to remain fixed in time. But over the years and decades that this bridge exists, in reality, that summer lateral earth pressure is going to get higher and higher and higher with each passing summer. And at some point, it can cause structural distress of the abutment. And again, this is not just some hypothetical possibility. It's actually been observed in practice. And again, it's because every annual cycle of expansion contraction begins at a larger neutral pressure state than the initial at-rest state. Well, because this abutment is kind of marching inward over time and getting locked in over time, you can actually also develop long-term net increases in stresses within the bridge superstructure due to the overall structure become increasingly locked in by the retained soil. Again, as the soil slumps downward, in the summertime, it's not going to magically unslump itself. And that's just the inelastic nature of soil. You know, the summer expansion is not going to magically push this soil back into where it was. It's going to stay slumped down, and it's only going to get worse over time. So the point is there's multiple structural engineering issues going on with this ratcheting. You could get a structural issue with the abutment. You can get structural issues with the bridge superstructure or deck as well. Well, bottom line is that the integral abutment bridge design concept needs to address two separate issues that are unique to this type of bridge as a consequence of eliminating the traditional bearings and expansion joints and creating these new geotechnical problems. Number one needs to address the fact that the summer seasonal increase in lateral earth pressure will increase over time. It's not enough to say, as has been done historically, okay, it'll increase in the summer, it'll be this or that. That's the end of it. Because most of those design pressure diagrams have been based on one cycle of thermal loading. It doesn't address what happens over 5 years, 10 years, 50 years. I mean, keep in mind, these bridges can have a design life of 100 years or more. So we don't look at the long term of what these pressures could be. Number two, we have the issue of the settlement trough that develops adjacent to the abutment. And whether you have an approach slab or not, you're going to develop pavement performance issues over time as this settlement trough continues to get deeper and expand laterally over time. So mitigation of these two issues, and these are separate issues clearly, earth pressure and surface settlement. requires two distinct actions. Number one, the retained soil needs to be self-stabilized independent of the abutments. You know, with the traditional jointed bridge, the retained soil could count on that abutment not moving for the life of that structure and holding it up. Well, with an IAB, the soil can no longer depend on the abutment because that abutment's going to go back and forth with the seasons. So the retained soil needs to be safe stabilized in some way. It can't count on the abutment. And there's two basic strategies to do this that I've come up with. One is to use mechanically stabilized earth reinforcement. And the other is to, instead of having soil, we use EPS block geofoam as a lightweight fill. And obviously the MSE is cheaper than the geofoam blocks, but it really depends on the nature of the underlying soils. If the underlying soils are soft and compressible, so you want to worry about settlement due to the retained soil, then it's going to be worth the money to use the EPS block geofoam as a lightweight fill. If the underlying subgrade is competent, then the MSE option is the way to go. The second action is to place geofoam compressible inclusion with fluid drainage capabilities. Again, you want to pick up any groundwater behind the bridge abutment between the inside face of each abutment and the now stabilized retained soil. And this compressible inclusion here is going to act as a de facto expansion joint. So I've seen cases where people try to leave a physical gap between the MSE and the abutment, and it doesn't work, because over time that gap is going to close up. It's going to attract debris. It's simply not going to work as in the long term as you want it to. But if you use a solid geofoam compressible inclusion, that compressible inclusion will expand and contract with the seasons and accommodate the seasonal displacement of the abutments in a controlled fashion, and in the process will also reduce the lateral earth pressures on the abutments. It will prevent this buildup, this ratcheting from occurring. Well, let me just illustrate simplistically the two choices then. If you have a fairly sound underlying subgrade, then to self-stabilize the retained soil, you'd place multiple layers of geosynthetic tensile reinforcement that will activate in a predictable fashion because you have a compressible inclusion here. So this is in a sense a ZEP wall application. Except in this case, the ZEP wall application is really to allow this retained soil to be self-stabilizing, and the compressible inclusion has the added benefit of acting as a expansion joint to handle the seasonal expansion and contraction of the abutment. Now, if the underlying subgrade is soft and compressible, which probably means your abutment is supported on deep foundations, then you've got to worry about settlement of the retained soil. So you're probably, this is a case where if you put in, I've just shown this as a simplistic wedge. Obviously, this is going to be stair-stepped into the soil. But you're probably better off creating a self-stabilized, lightweight zone behind the abutment. But again, you put the geofoam compressible inclusion in there to handle the expansion contraction of the abutment as a de facto expansion joint. And again, in both cases, the compressible inclusion also has a drainage capability. And I'll show you in a minute how we can make that happen. Well, to wrap up this segment on the compressible inclusion function, let me talk about material and product selection, because it's common to the rep wall, ZEP wall, and self-yielding applications. As I noted earlier in this presentation, the single most important issue currently facing the compressible inclusion function for reducing lateral pressures on earth retaining structures is the chronic lack of knowledge concerning operative, keyword here is operative values of the stress strain properties of the geofoam materials. And my experience is that both design professionals and academic researchers make some critical errors in this regard. Number one, they think that block molded EPS block is the only material, the only game in town to use for lateral pressure reduction, even for a compressible inclusion, because they're familiar with EPS blocks from the widely known use of EPS blocks as lightweight fill for earthworks, road embankments, things like that. So they probably don't even know about alternative geofoam materials such as resilient EPS or another material called glued polystyrene porous block. Both of these, both the resilient EPS block and the glued polystyrene porous block, were developed specifically for compressible inclusion applications and their use with earth retaining structures. The primary benefit of using resilient EPS block is, as opposed to just what I would call normal EPS block, is you get a much better compressibility and relatively low stress ranges of about 100 kilopascals, 2000 PSF. And this is certainly well within the stress range when we're dealing with lateral earth pressures on earth retaining structures. This is from an earlier publication of mine that you can find on ResearchGate. And this just shows under standard rapid loading. This is normal EPS block that had an initial density of 12 kilograms per cubic meter, about 3/4 of a pound per cubic foot, which is, in simple terms, about the lowest density / unit weight material you're going to find made, say, in the United States. Made consistently. Now, we see the very classical stress strain curve, right? Short-term stiffness, yielding, and then work hardening at higher strains. And by the way, these are engineering strains, not true strains. On the other hand, if you had resilient EPS of the same density, right? So we're comparing apples to apples here. Resilient EPS that has been subjected to an additional manufacturing step, we see how much softer the initial low stress response is. And again, 50 kilopascals, it's about 1,000 PSF, 1 KSF. This is the stress range that we're dealing with for lateral earth pressures on earth retaining structures. So notice under this stress range, and this is rapid loading, right? Again, I'm just keeping things simple for now. This is rapid loading. Notice how much more compressible the resilient EPS is than normal EPS. Right? If you're looking for a certain target strain, let's say you were looking for 10% strain in a given application. Well, notice that you would have to use a piece of normal EPS block that was what, about 5 times thicker than the resilient EPS to achieve the same amount of compression. And again, as I showed you earlier, when you're doing a rep or ZEP wall application, it's a force displacement displacement-based design. You're looking for a certain target magnitude of displacement. So you're looking for a certain stiffness. If you use normal EPS block, you've got to use 5 times the thickness to get the target amount of strain compared to the resilient EPS. very inefficient. That's my point, to use the normal EPS block. The other mistake is both designers as well, design professionals as well as academicians, use the small strain stiffness, the initial tangent Young's modulus of the geofoam material, which is completely irrelevant for compressible inclusion applications, because this is the stiffness up to 1% compressive strain. Well, it's irrelevant when you're designing for 10 or 20 or 40% compressive strain. You need to consider the large strain behavior, either secant or tangent as appropriate. The third mistake is results from conventional rapid loading tests, which are very, very rapid, strain rates of 10% per minute, are used to design compressible inclusions. Now, these very rapid strain rates, they're fine for doing quality control, quality assurance testing of the material. But if you're looking to see how this material behaves in 5 years, 10 years, 100 years, the modulus you measure in a 10% strain per minute test is clearly irrelevant, and you're not going to pick up any of the creep behavior. Well, to kind of put all these thoughts together, this is 12 kilogram per cubic meter, roughly 3/4 pound per cubic foot, normal EPS. It's the same curve I showed you previously, just looking at a smaller strain range that typically this is what we would be using, up to maybe 30+% strain. This is typically what we're going to see in compressible inclusion applications. Here we see the response in rapid loading. And here we see the equivalent resilient EPS in rapid loading. These are both I've shown you previously. And again, you see the point I was making. If you're looking for 10% strain under a certain stress level, you need about 5 times as much of the normal EPS to get that amount of compression. But now I want to introduce creep tests, right? And these are what are called isochronous stress-strain curves. They are created using creep tests. And essentially what these curves show is, okay, if this is the stress-strain behavior in rapid loading, if I now extended the loading to 10 hours, this would be the stress-strain curve. 100 hours, 1,000 hours. 10,000 hours is the minimum for creep tests. It's about 13 months, a little bit more than a year. For reference purposes, nowadays we prefer to do creep tests that extend to 15,000, 20,000 hours, so a little bit more than 2 years. So using creep test data, it's very easy to create these isochronous stress-strain curves, and I've done that for normal EPS. I've done it for resilient EPS. Well, we put this all together, and this kind of sums up everything I've been saying. Number one, in compressible inclusion applications, resilient EPS is the material of choice. Under the stress levels we're talking about that we see with lateral earth pressure applications, it is, for a given unit thickness, much more compressible than normal EPS block. Number two, we should consider the creep behavior. Again, creep is our friend. Generally, we've got to get out of this mindset we tend to have in civil engineering that creep is bad, creep is our enemy. And that's true. In a lot of structural and geotechnical design, creep is a problem. I'll be the first one to agree to that. But in reducing earth pressures, creep is your friend in compressible inclusion applications. So if we properly consider the behavior, not just under a test that is run in 1 minute or so, I mean, these tests here are 10% strain rate. These tests only took, 2 to 3.5 minutes to run. So this is the 3.5 minute behavior. We'd be a lot better off to consider 10 hours, 100 hours, 1,000 hours, 10,000 hours. At a given stress level, look how much softer the material behavior is if we consider the creep. So, sum it all up. In compressible inclusion applications, resilient EPS is preferred over normal block molded EPS. Number 2, consider an appropriate level of creep. Don't just use the rapid loading stiffness. Just to wrap up discussion, as I've said throughout this segment, in most applications, we want to provide for positive drainage of groundwater or infiltrating surface water, or possibly ground-borne gases as well. The ground-borne gas is a particular issue in some places adjacent to, say, basement walls of buildings. This is most easily accomplished using what is called glued polystyrene porous block, because this geofoam material is not only permeable and thus provides fluid drainage, but has a secondary function as a compressible inclusion. And we can incorporate this into a single product. This is a single commercial product that has, in this case, we have 4 inches or about 100 millimeters of resilient EPS. And then we have an additional 2 inches or 50 millimeters of glued polystyrene porous block. So the overall thickness of this product is 6 inches, 150 millimeters. And this one product is providing both of these materials contribute to the compressible inclusion function. Both of them contribute to thermal insulation. So if you have below ground space, say a basement of a building, you're going to get a lot of thermal insulation from this. And this same product is also providing fluid drainage of water and or ground-borne gases. So here you have one single product that's only 6 inches, 150 millimeters thick, and it's going to reduce your lateral earth pressures, it's going to thermally insulate your below ground space in the building, and it's going to drain your groundwater. And this just shows a very typical application. The dark brown you see here, this is just a non-woven geotextile that is factory bonded to the outside face. So here you see this 6-inch, 150 millimeter product that is simply glued to what is going to be a basement wall of a building. So this one product, and this product happens to come in panels that are about 4 feet square. So a little bit more than a meter square, about 1,200 millimeters square. Obviously very light, very easy to handle by one person. You don't need any heavy equipment to move it around. These are simply glued. This is just waterproofing, actually damp proofing, I think in this case, on the wall. And this one product is going to reduce the lateral earth pressures from the at-rest to the active state. It's going to provide thermal insulation for the below-grade space of this building, and it's going to handle any groundwater. You see it keyed into a drainage layer of crushed rock here. Well, that concludes this segment on lateral earth pressure reduction using the compressible inclusion function. Now I want to move on to the next segment, which deals with lateral pressure reduction using the lightweight fill function. Okay, so there are 2 ways in which the lightweight fill function can be implemented with earth retaining structures. One is the full depth placement. I've showed you this previously. And again, this is not meant to mean this can only be used with freestanding retaining walls. This is just a kind of a generic stand-in for an earth retaining structure. This could be many types of earth retaining structures. Anyway, we place the EPS blocks in a stair-step fashion. Again, that's very important, as we'll see why. We do have to leave a few feet meter or so at least at the top. And this is typically because we have a pavement system up here, so we need to be concerned about stresses from whatever vehicle is using that pavement on the EPS. Need to worry about differential icing where appropriate in the climate, as I mentioned previously. We can also have what's called partial depth placement. Now, it's very, very critical that if you do a partial depth placement, you always put the EPS blocks as close to the surface, again, typically 3 feet, a meter or so below the surface as possible. I've seen cases where people have done a partial depth placement where the EPS blocks were down here at the bottom of the wall, and then you had a rather substantial thickness of soil on top of it, and there was a serviceability failure of the foam. The foam was overstressed. This happened to be a highway project, a state highway project. That shall remain anonymous. That there were settlement problems, all sorts of litigation, et cetera, et cetera. So, you can't. EPS has remarkable load bearing. EPS blocks have remarkable load bearing for their extraordinarily low density, but you need to be smart about it. It only works if you kind of have the minimum thickness of pavement system up here to keep the stresses within the EPS blocks reasonable. Too much weight, in this case dead weight of soil, is going to cause excessive compression of the blocks. Now, either one of these can be used with new construction to reduce the cost of the earth retaining structure, or an existing earth retaining structure to improve its margin of safety. The partial depth is particularly useful with an existing earth retaining structure, because as I've mentioned earlier, when you have an existing wall, for example, you have a certain target of, look, this is the safety factor now, and I want to get it to this point. So you have a target of where you want to get the safety factor. That can often be accomplished just by putting a limited depth of EPS blocks behind that wall. Now, because the volume and therefore cost of the geofoam product is substantially greater for the lightweight fill function compared to the compressible inclusion function, again, with a compressible inclusion, we're talking about a panel that's anywhere from 6 to 12 inches thick, 150 to 300 millimeters. Whereas here, I think you could just use your imagination to see that we're talking about orders of magnitude greater volume of EPS and an appropriate increase in cost. But because the volume of EPS used in the lightweight fill function is substantially greater compared to the compressible inclusion function, to achieve the same degree of load reduction. That's the important thing. If you were to look at that beta parameter, which is a metric for load reduction, simplistically, you can achieve the same beta in either new construction or existing construction using the compressible inclusion function or the lightweight fill function. So again, the two functions, compressible inclusion, lightweight fill, these are competing technologies. They're not complementary. What I'm getting at is typically, at least in concept, the only time the lightweight fill function is, I think, defensible for use for lateral pressure reduction is when you want to minimize the vertical stresses on the underlying subgrade. And certainly there are many cases where that comes up. I personally have seen in the general area of New York State where I live that there's a basement wall, very deep basement wall of a shopping mall complex built on very soft ground. The wall and the complex were on deep foundations. Well, they wanted to reduce lateral earth pressures, but they also wanted to not have a lot of settlement. This was a parking area adjacent to the mall. So in that case, yes, the use of EPS blocks was completely justified because they wanted to achieve pressure reduction, but at the same time not overstress and cause excessive settlements of the underlying subgrade. So yes, there is a time and place when the lightweight fill function is the better choice for earth pressure reduction, but it's a very specialized situation. Unfortunately, theory and reality are two very different things in this case. Historically and to the present, the lightweight fill function, or at least the full depth placement, is much more widely known and used in practice compared to either the rep or ZEP wall versions of the compressible inclusion function, even though the compressible inclusion function is by far the more economical alternative in the vast majority of applications. This disconnect is despite the fact that the compressible inclusion function was identified through research and was publicized in literature before the lightweight fill function, at least in the English language literature. The predominance of the lightweight fill function in actual project usage is simply the result of the EPS industry, at least in the United States and probably elsewhere, actively promoting this function and not even mentioning the compressible inclusion function, as I've noted earlier in this presentation a couple of times. An additional significant issue is that much of the published literature concerning the lightweight fill function in earth retaining structure applications is unfortunately flawed to varying extents and for varying reasons, despite the fact that correct information has been published many times in the English language literature since the mid-1990s. And I say this on a first-hand basis as I authored much of this literature, either alone or with others. The bottom line, in summary, there's a significant disconnect between the state of knowledge and the state of practice when it comes to using geofoam to reduce lateral pressures on earth retaining structures. We've known since at least the mid-1980s that the compressible inclusion function exists, and research and experience indicates that it works. And even though the lightweight fill function was not known widely until well into the 1990s, it has come to dominate the state of practice. The single most significant knowledge flaw, in my opinion, concerning the lightweight fill function is understanding the correct geotechnical failure mechanism for determining the lateral resultant force acting on the earth retaining structure. It's important to reiterate that whether you use the compressible inclusion function or the lightweight fill function, essentially what the geofoam product is doing is attenuating the earth force between the soil and the earth retaining structure. So it's very important, or it's essential, to have the correct physical mechanism by which the geofoam achieves this load attenuation. We've seen with the compressible inclusion function, essentially the compressible inclusion is acting as a highly compressible spring. In the rep wall application, it allows the soil to self-mobilize its inherent strength. In the ZEP wall application, it allows the reinforced soil to activate the reinforcement and mobilize its inherent strength. So we need to define clearly what happens with the lightweight fill function. And unfortunately, there's been a tremendous amount of misinformation out there that continues to the present. Looking at the more widely used, more widely known full depth application, we see the stair step of EPS blocks. Still to the present, there are far too many people who just assume that somehow a failure surface magically develops through the EPS blocks, identical to the Coulomb type plane that is assumed to develop if this were all soil. And by the way, I should have perhaps mentioned this earlier. Despite what is said in textbooks and many other places, the Rankine solution is not and is never applicable to earth retaining structures. If you go into the development of Rankine's theory and solution in the 19th century, you find that it is a half-space problem. And as soon as you put a earth retaining structure in that half space, you violated the boundary conditions of the Rankine problem. The Rankine problem simply no longer applies. Coulomb, on the other hand, a century earlier in the 18th century, explicitly assumed the existence of an earth retaining structure, and that is part of his boundary condition. So the only solution would be the Coulomb solution, or if you prefer, one of the more modern 20th century enhancements, such as the Kakko and Carousel. In any event, this physically can't happen, right? You don't get a failure plane magically cutting through the EPS blocks. There's been extensive research largely in Japan in the late 1980s, early 1990s, that clearly showed what happens is the EPS blocks simply act as a physical extension of the earth retaining structure. And if you fit an average planar failure surface through the stair steps back here, as defined by an angle theta star, this in a sense becomes the de facto back of the quote-unquote retaining wall. And then you just calculate your earth pressures using Coulomb or Kakko Carousel, whichever solution you want. And then these earth forces act on this fictitious planar failure surface here. I think you could see two things I want to point out. First of all, if you don't stair step the EPS blocks, if the EPS blocks have a vertical face, and again, if you look at some older magazine articles, you will see this done. This theta star is 90 degrees, and in principle, the EPS does nothing to reduce the earth pressure. I think you could also see if this theta star angle was small enough, specifically the more Coulomb friction angle, or what in this case we would call the angle of repose, so perhaps 30 some odd degrees, the earth pressure would in fact be zero. And that is physically possible with the lightweight fill function. If you stair step this on a flat enough angle, there will be zero earth pressure that makes it to the earth retaining structure. And in fact, you don't even need the earth retaining structure anymore if you were building a new project. This would be what we call a geofoam wall, where the EPS blocks are inherently self-supporting, and all you would need would be a architectural covering, such as shotcrete or perhaps EPS, exterior insulation finishing system, on the face. But you don't need anything to hold up the EPS blocks, if you will. In any event, in the partial depth placement, things are a bit more complicated. Again, you always want to put the EPS blocks close to the surface, not down deep. The failure surface is not defined up front. The best we could say is that it varies has a maximum value, theta star max, defined by the EPS blocks because the failure surface can't cut through the EPS blocks. It has a minimum value defined by the angle of repose of the soil. So the critical angle is going to be somewhere in between. The easiest way I've found to solve this is very simple to solve nowadays. I happen to use Excel spreadsheet, the solver function, very efficient. It's what, if you look in older textbooks, it's what's called the trial wedge method. It used to be done manually. It's easy enough now to do by spreadsheet, and you simply find on a case-specific basis the critical failure angle. So in this case, this is significantly, in terms of mechanism, completely different than the full depth placement, the partial depth placement. In this case, essentially what the benefit of the EPS blocks is that they are replacing some of the soil within the critical wedge so that the weight of the soil wedge is less, and therefore the earth force that makes it to the earth retaining structure is less. Now, one of the things that has not been defined in the research to date is when does the partial depth placement transition to the full depth placement. Okay? If you stop and think about it, the two failure mechanisms here are very, very different. In the full depth placement, this is essentially the back of the earth retaining structure. And then you calculate the earth force in the usual way. Whatever failure surface wedge develops here in the retained soil, it's going to be all soil. Here, whatever failure wedge develops is going to be some soil, some EPS. So, completely different physical mechanisms. It's very, very subtle. You may need to stop and think about it a bit. Here, the earth force reduction is occurring because you flatten the back of the earth retaining structure, if you will. You have a wall that has a flatter back, and therefore the earth force is going to be less. Here, the earth force reduction occurs because the weight of the failure wedge is less. So these look like the same problem, but the mechanism by which load attenuation on the earth retaining structure is occurring is completely different. This is strictly a weight issue. Now, one thing that has not been done to date in research and published in literature is when does this transition to this? Okay, when does, obviously at some point, if you keep making the partial depth placement deeper and deeper and deeper, you're going to transition to a situation where now this failure mechanism is going to govern. At what point this transition occurs has not, to the best of my knowledge, been developed and would be an interesting area of research. Now, in practice, as I said earlier in this presentation, when you use geofoam to reduce earth pressures, it's never an all or nothing proposition. And the same is true with the lightweight fill function. What I'm showing here is cost, and there's a separate cost, and this curve is set up as if one were designing a new installation. It's a little bit different, as I'll point out in a minute, for an existing structure. If you're building a new earth retaining structure, you have a cost curve of the earth retaining structure. This is the baseline case of no EPS. This is the extreme case of so much EPS that the earth force is zero and you don't need an earth retaining structure anymore. And here's the cost of the EPS blocks. Now, I'm not saying that these are nice smooth curves as I've shown them here. This is really a qualitative depiction. So here cost is increasing on the horizontal axis. There's two axes here. One is increasing. This is the volume of the EPS blocks, and the other is decreasing. This is the angle theta star. Or this is increasing to the left here. Volume of EPS blocks increases to the right. Theta star increases to the left, with 90 degrees being the limit here, and the angle of repose being down here. So the point I'm getting at here is as theta star decreases, so as this angle up here gets flatter and flatter and flatter and flatter, right? This failure surface gets flatter and flatter. The load transmitted to the earth retaining structure decreases, so you need a less expensive wall, but of course the cost of the EPS blocks increases. Now, in principle, if you combine these two costs, there is some sweet spot, as they like to call it in a tennis racket. There's a sweet spot where these costs minimize. And this sweet spot, if you will, has to be determined on a project-specific basis. Now, if you have an existing earth retaining structure, things are a bit different because in addition to considering cost, you also have to consider that if you're trying to remediate an existing earth retaining structure, and again, the very common example I used earlier was you have an existing gravity wall, let's say it was never designed for earthquake, you want to upgrade it to be stable in an earthquake. there is some minimum safety factor you're now trying to achieve. So the process here with an existing structure becomes a bit more complicated, because it's really not so much the cost of the earth retaining structure. The earth retaining structure is there. Really what you have to add is another vertical axis that shows how, as the cost of the EPS blocks goes up, the safety factor of the earth retaining structure goes up as well. So with an existing earth retaining structure, the challenge is to find what's the minimum amount of EPS blocks you need to achieve some target value of safety factor. Well, that includes the lengthy discussion of lateral pressure reduction. Now I want to discuss vertical pressure reduction. And I've divided this up into topics. And again, as I mentioned at the outset, I've divided this into applications as opposed to functions. Because as we'll see in these different applications, we can and do make use of multiple geofoam functions. So with lateral pressure reduction, it was convenient to break it into a discussion of compressible inclusion function versus lightweight fill function. Now when we're talking about vertical pressure reduction, it is convenient to talk about application, because in those applications, as you'll see, there are multiple geofoam functions that we can make use of. Just to give you an overview of what I'll be talking about, geofoam can be used in a variety of applications where the reduction of vertical earth pressures on some structural element is the primary, if not sole, objective. And because such applications can be multifunctional, including thermal insulation, fluid drainage, in addition to pressure reduction, as I said, it's useful to organize this discussion along application as opposed to functional lines. So the applications I'm going to consider are below-grade structures, underground conduits, and structural systems that are affected by expansive soil and rock. Beginning first with below-grade structures. Structures in this category are generally constructed of Portland cement concrete, or rectangular in cross-section, and have a width that is greater, often substantially, than the depth below the ground surface. So we're talking here about relatively shallow structures. Typical applications involve commercial space for office or business, parking garages, cut and cover tunnels. Here, the EPS block geofoam is the product of choice, and it's used as a lightweight fill material. This just shows the general concept. You have a fairly shallow structure, and rather than design the roof slabs, which can often have relatively large open spans for the earth loads, is to simply place an assemblage of EPS blocks above the roof slab. Again, needing to consider things like differential icing, live load stresses, etc. You're always going to need some thickness of material on top of the EPS blocks. It's of interest to note that thermal insulation can be a useful and significant secondary function for these types of structures. And that's because they are often shallow enough so that thermal loading of the roof slab can produce effect on the side walls, very similar to the self-yielding rigid earth retaining structure problems that I discussed previously in some detail. I noted previously when I talked about differential icing that the near surface environment is very dynamic in terms of where the interface is between thermal effects from the atmosphere and thermal effects from within the earth. So depending on the thickness here, this roof slab can heat up in the warmer weather. It's going to expand, and obviously this is a statically indeterminate structure. So it could push the side walls out and increase lateral earth pressures, really very similar to the summer season loading on an integral abutment bridge that I talked about in detail previously. Clearly, if you have an assemblage of EPS blocks on the roof slab, that is really going to mitigate any thermal effects. There might be some additional benefit to using compressible inclusions composed of resilient EPS block with the fluid drainage capabilities along the sidewalls, because normally these walls are non-yielding, so it should be designed for the at-rest earth pressures and perhaps some compaction effects. But if you place a compressible inclusion here, as a minimum, you could reduce this to the active earth pressure state, as well as provide positive drainage along these side walls. I guess if you really wanted to go all out, you could put geosynthetic reinforcement here and have a ZEP wall application. But certainly as a minimum to create a rep wall application is quite reasonable. Probably the greatest use of geofoams is for vertical pressure reduction is with underground conduits, simply because these are so ubiquitous. Structures in this category includes are typically circular in cross section and either preformed metal elements or precast concrete. They can also be square or rectangular in cross section, in which case they're usually either cast in place or precast concrete. And here we make use of the compressible inclusion function using resilient EPS block as the geofoam material of choice. The problem here is one of negative arching. This is a classic case of negative arching. I mean, this goes back to the seminal work of Spangler and Marston, Handy, going back to the beginning of the 20th century. And that's because very often, especially when these underground conduits are constructed of concrete, they are hard spots, if you will. So the vertical pressures on the crown or the roof slab are typically greater than the overburden stresses by a factor of 50 to 100%. And this is based on probably a century or more of observation and research. Now, of course, you could design the conduit for this, but the question then becomes why would you when you can relieve those pressures very easily? So by placing a geofoam compressible inclusion, again, we're talking about a fairly, if you use the right material, again, the emphasis here is on the right material. If you use, say, resilient EPS block, these compressible inclusions generally need to be no more than a few inches, a few tens of millimeters thick. If you look at the literature, you will see people using EPS blocks several feet, a meter or more thick above the crown or roof slab. And the reason they need to do that is that EPS block normal EPS block is a terrible choice for this application. As I showed you previously, under the relatively low stresses that we're talking about, you'd have to use regular EPS block maybe 5 to 10 times thicker than if you would use resilient EPS block. So this is just a modern version of Marston's classical imperfect ditch concept. Back in Marston's day, people did things like placing loose soil or a bale of hay or straw, something like that, above the crown or roof slab. Nowadays, we have much better, more modern alternatives to achieve the same thing. And you can achieve some very impressive reductions. So now, with the compressible inclusion, the vertical pressures on the roof slab or crown are less than the overburden stress by a factor typically has been found of 20 to 50%. So the overall reduction, if we go from the negative arching case to the positive arching case, you could reduce the loads by a factor of 3 to 10, which is quite significant. I mean, considering that when you build underground conduits, you need a very relatively extensive length of conduit. So if you could reduce the load demand on these conduits, you can achieve some significant cost savings because of the volume of conduit that you're placing. In some cases, with a large box type culvert, as these are called, you may find some additional cost benefit to using compressible inclusions along the side walls as well. And again, these would be resilient EPS block. So this would help to reduce the lateral pressure on these structures to achieve some further economy. As I said, you do see, if you look at literature, I mean, people use geofoam to reduce vertical pressures on underground conduits quite often, but you'll often generally see them use normal EPS block. And this continues to the present. It's much less efficient and therefore much, much more expensive because, as I said, you may need 5 to 10 times the volume of geofoam product to achieve the desired magnitude of compressibility and concomitant load reduction on the conduit. So, you know, you're spending a lot of your client's money if you're using normal EPS block for this application. We can kind of tweak or enhance this a little bit if you are in an area with significant seasonal ground freezing. A lot of times underground conduits are relatively shallow. When you have a pressure conduit, such as a water main or whatever, that's operating under pressure, it does not inherently need to be at a great depth. If you have a gravity sewer, you may have to have a fairly significant depth to achieve the gradients that you want. But we can have seasonal ground freezing to depths of the order of 10 feet or 3 meters. Beyond that, you tend to transition to areas of permafrost or semi-permafrost. So the rule of thumb is that seasonal ground freezing in the extreme could go to depths of 10 feet, about 3 meters. So we can make use of the thermal insulation function to reduce installation costs. And there's two different applications. One is called frost shielding and the other is to prevent frost jacking. Talking first about frost shielding, this is used to reduce the embedment depth of water-bearing conduits such as water lines and sewerage, while functioning as a compressible inclusion as well. So you really get two benefits here. You reduce the cost of the underground conduit product because you have a compressible inclusion and therefore reduce the pressures that you have to design the conduit for. But then you get a construction cost saving because you can bury this conduit as a significantly shallower depth, and I'll show you how. And again, considering that seasonal frost depths can extend to as much as 10 feet or 3 meters, if you have to contend with rock excavation to achieve this, this could be extremely expensive construction-wise. So normally with a water-bearing underground conduit, you have to place it below the seasonal depth of freezing. But if you have a thin layer of geofoam, and again, here we're talking about a layer of resilient EPS, that's probably no more than a couple of inches, maybe 50, 75 millimeters thick. We're talking about a very, very thin product here. Maybe 2 to 3 inches, no more than 4 inches, so 50, 75, no more than 100 millimeters thick. You're going to get a load reduction to design the conduit itself from compressible inclusion, but as you can see, you could bury it at a much shallower depth because this is now going to permanently change the pattern of seasonal ground freezing. And this has been researched quite extensively. I know here in the United States by the U.S. Army Corps of Engineers, Cold Regions Research Laboratory up in New Hampshire. They have done test installations of this that have worked very well. You will see in the research that people have tried to go a step further and place the geofoam material along the sides here as well. You get a little bit more reduction of ground freezing. Personally, I think this comes at the cost of, having spent many decades in professional practice. I'm very attuned to what we call constructability. Something that not only looks good on paper, works well on paper, but can be reasonably constructed. This can be reasonably constructed. These side walls, these are much more fussy and difficult to construct properly. But I do want to point this out because you will see this in literature. The second benefit is to prevent what we call frost jacking. And this is when we have a conduit, say some type of culvert under a highway embankment is a very classical example. You have a culvert of some kind. It doesn't have to be circular. You have a culvert of some kind under a road embankment or rail embankment. And that culvert is open on both ends to the atmosphere. So in areas of seasonal freezing, the air in here is going to get cold. And as a result, you're actually going to get a local depression in the depth of seasonal freezing. If your normal depth of seasonal freezing is, say, a meter, roughly 3 feet or so, you're going to get that meter or 3 feet below the culvert. So this is not insignificant. Well, what happens is, due to frost heaving that occurs, this culvert will literally get jacked out of the ground and will bulge up on the ground surface. So if this is a road surface, you're going to get a very distinctive bulge here, typically several inches, several tens of millimeters. If this is a rail line, you're going to get a bulge in the alignment. You're going to get a hard spot that's going to affect the rideability. Well, here again, we use a relatively thin panel of geofoam, again, no more than a couple inches, a few tens of millimeters, and this is now going to depress the seasonal freezing, so you will not get the frost jacking. And by the way, this will function as a compressible inclusion. I showed you a few slides earlier that normally when we use a compressible inclusion above an underground conduit, we place it above the crown or roof. And that's simply because it gets the job done and is the easiest place to construct it. It's really a constructability issue. But compressible inclusions work very well underneath the conduit. The only problem is now the conduit is going to settle perhaps a fraction of an inch, several millimeters. So, but certainly if you're looking to prevent frost jacking, this is where you have to place the geofoam product. Well, the last application I want to talk about for vertical pressures has to do with expansive soil and rock. And as we know, this is a very significant problem globally. I remember reading some years ago that if you look at all the natural disasters that occur in terms of cyclones, hurricanes, tornadoes, floods, etc., and if you annualize the cost of these, expansive soil and rock is the biggest natural disaster in the world. Well, because expansive ground is such a significant global problem, it's no surprise that major structures need to be designed against this problem. And a very common situation is to have a structural slab supported on grade beams that frame into deep foundations that are founded below the active zone of the expansive ground. So in this situation, it's highly desirable to isolate the structural slab from the underlying ground to the greatest extent practicable. And this is to minimize the uplift earth pressures that can develop during the life of the structure. As I indicated earlier with expansive ground, I noted that things that are done during construction, such as covering over the ground surface, will change the moisture regime around the structure and beneath the structure. And these changes can then cause long-term changes in the uplift pressures. Well, this application is a real technical challenge because on the one hand, you would think you'd want a compressible inclusion that was compressible as possible to minimize this uplift pressure piece of S. But constructability dictates that whatever you put in here has to be strong enough to support the reinforcing steel, the rebar, and fluid Portland cement concrete during construction of the slab. So you really have competing technical needs here. Well, the basic solution, of course, is to simply place a geofoam product beneath the structural slab. But this product has to be, it can't be normal EPS block, it can't be resilient EPS block, it can't be any of the products we've talked about previously. It has to be designed to support the structural slab during construction, but then to the best it can, in a sense, disappear or minimize after construction to be highly compressible and accommodate potential uplift pressures. Well, as with the compressible inclusion function for lateral pressures, this is a soil structure interaction problem, and it involves stiffnesses, not strengths. So if we look at a simplified picture of expansive soil rock behavior, we know that if we have the one limiting condition we call fully confined. This is equivalent to when we talked about thermal loading previously. If you have a structure that cannot physically expand, you're going to maximize the forces and stresses in the structure due to thermal increases. Well, it's the same thing here. If you have a fully confined system, you're going to have maximum pressures from the expansive ground. Well, the other limiting case is what we call the free swell case. If you allow the ground to expand as much as it wants, the pressures will, of course, be zero. And it's the same thing to when we talked about thermal loading. If you have a structure such as a traditional bridge deck that can expand or contract as much as it wants on the bearings and expansion joints, there's not going to be any thermal loading developed in the bridge deck or superstructure. And there is some, in theory, nonlinear relationship between these two cases that is depend on the particular material we're talking about. So very similar to the compressible inclusions for lateral pressure reduction, essentially by now introducing compressible inclusion in the problem, which is somewhere between fully confined and free swell, we're going to have some pressure, but obviously we're able to reduce it from the extreme pressures of a fully confined state. And although we're not able to, in general or in principle, to change the ground response, of course the compressible inclusion is something we can design. But again, the challenge here is this compressible inclusion. It can't be extremely compressible. It's got to have enough stiffness to be able to construct the slab. Again, as I already noted, this application has some unique technical requirements. It's got to be sufficiently stiff to support the weight of the rebar and concrete during construction of the structural slab. And then once the slab is hardened, it's got to be as compressible as possible to minimize the vertical pressure transmitted through the geofoam to the structural slab. Well, there's been actually over several decades, going back to at least the 1990s, if not a bit earlier, there's been research in several countries, Canada and the United Kingdom come to mind, where they've developed EPS-based geofoam products that are unique to this application. And these products have evolved over time. You know, people have tried things, they say, well, this works, but let's try to develop something that works even better. So there are some proprietary products that can be found on the market. I know these Canadian products, for example, are widely available throughout the US. One thing of particular note with these products is that they're cost effective for the entire range of engineered construction. They have been used on world-class mega projects, and they've been used on single-family houses. And I'll just show you a couple of examples to show you the fact that these products can be cost-effective on the entire range of engineered construction. These are not just a big project type of material. You may not recognize this, but this is actually the famous Channel, the rail tunnel that was constructed between England and France. And they had, in sections of the Channel, they had problems with expansive ground that they had to contend with. And here you see the section of the tunnel under construction, and you can see the deep foundations have already been installed. And what you see here is a Geofoam product. This is one of the early products used in the UK that is being installed before construction of the structural slab that will be supported on these deep foundations. Now, this particular product in the UK is colored pink. That's why it doesn't look purely white. It is artificially colored pink. And as I note in my primer on geofoams, expanded polystyrene is inherently white in color. And that's why if you see the ubiquitous foam coffee cup, it is white in color. EPS is inherently white in color, so is resilient EPS. But you can add a color into it. You can make it any color you want. It's not a big deal. Anyway, so this is a product that they used here. This is kind of a second generation product that's available both in the UK and Canada. This happens to be a project in Canada, in Winnipeg, Manitoba, a water treatment plant, again with expansive ground. And I'll show you an up-close photo in a minute, but here you see the tops of the deep foundations have already been installed, and they're placing the Geofoam product with a underlayment on which then workers will come in and set the rebar and pour the structural slab for this tank. And here's an up-close view. Here you see the tops of the deep foundations. This is kind of like, it's a very ingenious product. As I said, there's versions that have been developed in the UK and versions developed in Canada. The Canadian version is available throughout the US. It's kind of like an egg crate. It's very, very clever. It's kind of like an egg crate. And you see the pieces here. They come factory cut in this sawtooth arrangement. And these are just clipped together with metal clips in the field. You put a underlayment. This looks like OSB oriented strand board sheets here. And this is just to support the rebar chairs and the rebar and fluid concrete. So this is stiff and designed intentionally just for this application. This is stiff enough to support construction. Comes in different grades depending on how thick a slab you're going to use. And then it's designed to sacrificially crush if the ground expands. And this just shows the other end of the spectrum. This is the same Canadian product actually being used for a single-family house in Colorado. So I include this just to show you that this can be cost-effective to use for single-family housing or condos or things like that. So here you see the site preparation. The deep foundations have been installed. I don't have the details of what was used here. This looks like it might be some type of helical pile may have been used. This house has a full basement, which normally you wouldn't see in areas with expansive ground. and the product starting to be delivered to the site. And here you see the contractor has placed the product, and again, this is just a underlayment board that is being used so that they can set the rebar and pour the concrete for the finished slab. And here you see the rebar has been placed, set on chairs. These are the penetrations for the various utilities, plumbing lines, etc., and getting ready for the concrete pour. So certainly, given the global breadth of problems related to expansive ground, we have products geofoam products that can be used very successfully in these types of conditions for both the very largest and the very smallest types of projects. With that, I'd like to bring this presentation to a close. I'd like to say first and foremost, thank you for your time in viewing this presentation. Hopefully it has been worthwhile for you. You've learned a few things, perhaps clarified a few things for you. As I mentioned early in the presentation, back in 2018, I wrote a monograph that goes into great detail on the subjects that I talked about in the presentation today, especially using geofoam to reduce lateral pressures on earth retaining structures. I go into detail in terms of analytical methods and experiences, things like that, that I certainly could not get into in this presentation, which was long enough. Before closing, I'd just like to point out the back cover of that monograph has photos of, I think, an interesting variety of applications of geofoam for lateral pressure reduction. This was a very early project here in the United States that used EPS block geofoam to reduce lateral pressures on a below-grade parking garage. As I pointed out during the presentation today, in those early projects, people did not realize they needed to stair-step the EPS blocks into the retained soil. They simply stacked them with a vertical face, at an angle theta star of about 90 degrees. Nowadays, we would know better to stair-step things. But this was an interesting application where use of EPS blocks as opposed to a compressible inclusion was the better choice. This site had soft soils, and all the structures were supported on deep foundations. So in addition to reducing lateral pressures on the below-grade walls of the parking garage, they were concerned about settlements outside, because this area here was all at-grade parking. So this was actually a good choice in this case, because by using EPS blocks, they were able to minimize the settlements that occurred outside the structure. But as I said, nowadays we would certainly stair-step these blocks. But nevertheless was a successful project. This was an interesting little project in Idaho where they used EPS blocks as a lightweight fill behind a soldier pile and lagging wall. Again, this was use of EPS blocks as opposed to, say, a compressible inclusion made sense because they were concerned about slope stability here. This was an abutment actually for a bridge, a small pedestrian bridge. So they were concerned about slope stability. This does point out one of the benefits of using geofoams in general for many different applications is that you could place it in all types of weather. Here you see them placing these blocks in the middle of winter with snow on the ground. And that certainly would have been impossible to do with traditional earthwork or mechanically stabilized earth. Anything requiring manipulation of soil was very easy to take care of with the EPS blocks. This was an interesting project. Actually, I visited this site 20 plus years ago. This was the first recorded use of EPS block geofoam in general in Chile. This was an integral abutment bridge that had been built to replace a traditional jointed bridge. The site was very interesting because it's in the southern part of the country that was very close to the epicenter of what many people feel is the largest known earthquake in human history back in 1960. So the site had very severe, obviously, seismic requirements, very soft soils. So they were using EPS block geofoam to minimize the weight of the embankment on the underlying subgrade, as well as to reduce lateral pressures on the abutments that you see here. This project was in Japan, and it's interesting because it illustrates use of EPS block geofoam to reduce lateral pressures for a flexible earth retaining structure, in this case an anchored bulkhead. If you've ever done analyses of anchored bulkheads, you know that under gravity loading, the toe kickout tends to be the most critical failure mechanism, whereas under seismic loading, both analyses as well as experience indicate that tie rod failure tends to be the critical failure mode. So this was a seismic enhancement of this wharf to this marine facility, obviously, to reduce the stresses around the tie rod level and increase the seismic stability. This was a very early, in fact the earliest that I know of, use of EPS geofoam, in this case the geotech geo-inclusion, behind the deep basement of a commercial building in Kansas City, Missouri, or Missouri if you prefer that pronunciation. This is a more distant view of a photo that I showed you close up earlier in the presentation. So in this case, the rep wall application was being used solely to reduce lateral earth pressures on the deep basement of this building from the at-rest to the active state to reduce the cost of the exterior basement wall. This is the composite, geocomposite product I showed you earlier. It consists of several inches of resilient EPS as the primary component of the compressible inclusion that is factory laminated to 2 inches or 50 millimeters of glued polystyrene porous block that acts as the drainage layer, and it has a dark facing because that is the factory applied non-woven geotextile that serves as a filter for the drainage layer. So this total product is 6 inches or 150 millimeters thick. Very easy to place. As I said, the panels were 4 feet square, so a little bit more than a meter square. Very easy for one person to place, and the use here was to achieve cost reduction in, as I said, the exterior basement walls. And this final case history slide is for a semi-integral abutment bridge in Virginia in the United States. I did not get into semi-integral abutment bridges at all in my presentation. I mentioned them, but I did not get into them at all. They have many of the similar problems to integral abutment bridges in terms of the fact that these short stub embankments are moving with the bridge deck in this case due to seasonal thermal changes. So you see that the same composite product, the geotech geo-inclusion, is being used here. Again, 4 inches, 100 millimeters of resilient EPS, 2 inches, 50 millimeters of glued polystyrene porous block, and you see the dark colored non-woven geotextile. It's folded back here. It's going to be folded over the top to provide filtration along the top edge of this installation. This project has been documented in the published literature by employees of the state of Virginia, so you could read more about the specifics of this project if you're interested. And of course, all of these projects are specifically referenced in this monograph. Copies of my monograph are available worldwide on a print-on-demand basis, so generally the turnaround is fairly short, a few days, a couple of weeks at most. It can be ordered, as I said, worldwide from any online bookseller. I have to laugh because I found by accident that even places like Walmart and Target here in the United States will sell this book. In any event, so all you need to do is go to your favorite online bookseller, or if you're in academia, to ask your academic librarian to obtain a copy. Here's the ISBN 13 number. So using this international number, you can easily find this book. So with that, I will close out this presentation. And again, I say thank you and goodbye.